Hello viewers, Argand Diagram taking you through the story of A-level pure mathematics. And this video I'm going to go through the topic of complex numbers. So this video is suitable for students in both Senior 5 and Senior 6, offering principal mathematics as part of their combination. So before we start, let's first look at the course outline. So math paper 1 is divided into 5 parts. The first part is algebra, where 2 questions come in section A and 2 in section B, and these are the topics. Next is trigonometry, where 1 comes in section A, 1 in section B, and these are the topics. Next is geometry, where 1 comes in section A, 1 in section B, and these are the topics. Fourth is vectors, where 1 comes in section A and 1 in section B, and these are the topics. And lastly, calculus, where 3 come in section A and 3 in section B. So the topics which are ticked are already covered. So the entire calculus has been covered, entire vectors has been covered, entire geometry has been covered, and also entire trigonometry has been covered. So this video will be on complex numbers, and that will mark the end of math paper 1, after which we shall concentrate on math paper 2. So some of the videos of math paper 2 are available. So what I'm going to do at the end of this video, instead of putting end screens of math paper 1 topics, I'm going to put the end screens of math paper 2 topics. There will be mechanics, statistics, probability, and numerical methods. So instead of putting topics for paper 1, I'll put topics of paper 2, because some of you have been consulting whether math paper 2 is also available on this platform. So math paper 2 is also available on the platform, although it is not complete. So now that we have finished paper 1, we are going to concentrate on paper 2, and we also complete it. So let's start with complex numbers. So complex numbers are numbers which are written in the form this, where it's a plus bi. So this I is very vital, and that's the core of this topic. So a plus bi, a is a real part and b will be the imaginary part. Now why is it imaginary? It is because it has this I component. So the part which has the I component is called the imaginary part, and the part which does not have is called the real part. Now these a and b are constants. It can be 2, it can be 3, it can be an integer, it can be a whole number, it can be a fraction, it can be anything. Now what does this I represent? So this I is used to represent a negative square root of 1, a square root of negative 1. What does that mean? It means that when I square both sides, I'll come up with I squared equal to negative 1. So both this and this are very vital. So when you come across I squared, just know that it denotes negative 1. And when you come across I, just know that it represents square root of negative 1. So we shall see how important these two values are as the video goes on. So what does that mean? It means that a purely imaginary number is a number whose real part is equal to 0. So this concept is also very important. It should be seen under locus still in this video. Then also a purely real number, it means that the imaginary part is 0. So purely imaginary, it means that this one is 0, and purely real, it means that the imaginary part is 0. So now let's start with arithmetics of complex numbers. Arithmetics mean addition, division, multiplication, and subtraction. So we shall consider two complex numbers, one which is z1, which is a plus bi. Another complex number will be z2, which is c plus di. How will they be added? So to add two complex numbers, z1 and z2, the concept is that the real part of z1 is added to the real part of z2, and the imaginary part of z1 is also added to the imaginary part of z2. It's somewhat like adding two vectors, because when you add two vectors, you add component by component. So the I component is added to the I component, and the j component is added to the j component. So here it means that when I add, it means that I'll get this added to this, and then also get this and add it to this. That's how they add to vectors. So the outcome will be as follows. So this plus this gives you this real part, and this plus this gives you the imaginary part. Don't forget the I, because it is what distinguishes the imaginary part and the real part. So that was addition. What about subtraction? So subtraction, to subtract two complex numbers is somewhat similar to addition. So you do the same real part alone and also imaginary part alone. So when I want to subtract, when z1 is subtracted from when I want to subtract z1 from another complex number z2, it means that the real part of z1 is subtracted from the real part of z2, and the imaginary part of z1 is subtracted from the imaginary part of z2. Therefore, if I have z2 minus z1, I'll first write my complex number of z2 and also complex number of z1. Note that we are using brackets, so these brackets are very vital, because if you remove them, this and this may confuse you. So what I'm doing that, I'll come and subtract this minus this gives you the real part, and this minus this gives you the imaginary part. Don't forget the I here. Next will be multiplication. So we are first dealing with writing all the arithmetics. After that we shall see the worked examples, of course from UNEB. So part C is multiplication. So if I have two complex numbers and I want to multiply them, I'll use the knowledge of opening brackets which was acquired in algebra. But as I do that, I must bear in mind that I squared is equal to -1. So let's do that and see how to multiply two complex numbers. So like we did in algebra, this one will multiply this and this to give you this, and also the whole of this will multiply this and this to give you this part. After that we shall open brackets further. This times this gives you this, then this times this gives you this, and this times this gives you this, then this times this gives you this. So from there I'll come and simplify. This gives you AC, and this gives you ADI, and this gives you BCI, and this gives you BDI squared. Now this is why I told you that you must be keen to remember that I squared is equal to -1. So what I'm going to do, I'm going to replace this I squared with -1 to come up with that. And after that I'll rearrange. So complex numbers, at the end you have to rearrange real part alone and imaginary part alone. So here I'll come and say this one, because I've removed the I, it is no longer imaginary part, is now a real part, because it no longer has an I. So this and this will be grouped together to give you the real part, then this one will give you the imaginary part. So always remember, complex numbers, at the end of everything you must collect like terms, real part alone and imaginary part alone. So here we have seen multiplying two complex numbers, but sometimes they can give you a constant and they want you to multiply it with a complex number. So what do? You simply open brackets. This times this gives you this, and also this times this gives you that. So that is how they multiply a constant with a complex number. So we have seen addition, subtraction and multiplication. Now let's go to the last part of division. So yes, the division of two complex numbers requires knowledge of what we call a complex conjugate. Now we have got another term, complex conjugate. What is this conjugate? So let's first talk about conjugate, then at the end we shall talk about division. So a complex conjugate is a complex number of a complex number z is noted by z bar. So when you see z bar or w bar, it means that that is the complex number of this given letter. So in this case we have z bar, meaning that z bar is the complex number of, is the complex conjugate of z. And how is it got? It is got by changing the numerical sign of the imaginary part. Note that we only change the numerical sign of the imaginary part, not the real part, it is imaginary part. So let's try to illustrate that with a table. So we shall have a complex number z, and it will have 4 values. So z can be this, or z can be this, or z can be this, or z can be this. So those are the 4 ways of representing a complex number. Here, the first part, both the real and imaginary part are positive. Here, the real part is positive, imaginary is negative. Here, the real part is negative, imaginary is positive, and here both are negative. So those are the 4 ways a complex number can be written or represented. Now let's get their complex conjugate. Remember, we said to get the complex conjugate, you change the numerical sign of the imaginary part. So in this case, the numerical sign of the imaginary part is positive, meaning that the conjugate will have a minus. Here it is minus, meaning that the conjugate will have a plus. Here it is plus, meaning that the conjugate will have a minus. And here it is minus, meaning that the conjugate will have a plus. So as simple as that. So that is how they get complex conjugate. Now that we know that, we shall go back to our division, and we shall say that when I'm dividing 2 complex numbers, it involves rationalizing by multiplying through the numerator and denominator by the conjugate of the denominator. Remember, when you are dividing 2 complex numbers, there will be a complex number in the numerator and also complex number in the denominator. So what you do, you look at the complex number in the denominator and get its conjugate. So in this case, the conjugate of this will be c minus di. After getting the conjugate, you multiply both the numerator and denominator with that complex conjugate. Now the process of multiplying both numerator and denominator is what we call rationalizing. I think remember that word rationalizing under the topic of SADS. Others call it an innocent expression. So after that, we shall remember this is now multiplication, so we have to multiply. So when I multiply this with this, I'll come up with this. I think by now you know how to multiply 2 complex numbers. But when you look at the denominator, we are going to get a difference of 2 squares. So difference of 2 squares means we'll come up with c squared minus di squared. But from there, I'll remember that this is d squared times I squared, and I squared is -1. So what does that mean? It means that the whole of this becomes negative d squared, and when the negative with this one will give you a positive here. So for complex numbers, when you remove the I, it means that now this is plus. That's how difference of 2 squares in complex numbers is carried out, because I squared means is equal to -1. So the -1 cancels with this negative to give you a positive. Now then, let's go through some of the worked examples. So question 1 says, if z1 is this, so here we forgot an I. Make sure we put it there. z1 is -3 plus 4i, and z2 is 7 minus 5i. Find Roman 1 2z1 plus 3z2, Roman 2 4z1 minus 5z2, Roman 3 z1 z2, and Roman 4 z1 over z2. So remember, I told you put an I here to make it an imaginary part. So we shall start with z1. Sorry, the Roman 1. Roman 1 says 2z1 plus 3z2. So what you do, you are going to substitute for z1 and also for z2. After that, now this one is multiplying a complex number with a constant. So this 2 multiplies this and also this to give you this. Then also this 3 multiplies this and this to give you this part. Then after that, we're adding 2 complex numbers, so you collect like terms, real part alone. So -6 plus 21 gives you positive 15. Then positive 8i minus 15i gives you -7i, and that would be the value of this which they wanted. Now let's go to Roman 2. Roman 2, it is subtraction, so still do the same. First multiply the constant through the complex number to give you this part. Then also this constant through this to give you this. Now remember there's a negative here, so negative and this gives you negative, then negative and this negative gives you a positive here. Then from there we collect like terms. Negative 12 minus 35 gives you negative 47. Then positive 16i plus 25i gives you 41i, and that's what they wanted. Now we shall go to Roman 3. So Roman 3 is a multiplication. So multiplication you have to open brackets. So negative 3 times 7 gives you negative 21. Negative 3 times negative 5i gives you positive 15i. Then also 4i times 7 gives you positive 28i. Then 4i times negative 5i gives you negative 20i squared, but remember this I squared is negative 1, that is why here you see plus 20 and the I is no longer there because I squared is equal to negative 1. Then next is collect like terms. This with this gives you this real part, and this with this gives you the imaginary part, and that's what they wanted. So now we shall go to Roman 4. Roman 4 is division, and division, remember we said you have to first multiply the numerator and denominator by the complex conjugate of the denominator. So this is the denominator, and this conjugate will have plus here, that's why you see plus here, and we apply up and down by that complex conjugate. The next is open brackets. When I multiply this with this, I'll come up with this. I believe by now you know how to multiply two complex numbers. Then this one is difference of two squares, but remember we said difference of two squares under complex numbers will have a plus here because the I squared is equal to negative 1. That is why you see here you see a plus, and here there is no more I. The next is collect like terms. This with this gives you that, and this with this gives you this. Then this plus this gives you that, and that will be the answer. So for complex numbers, you must ensure that the denominator does not have any imaginary part. Remember, ensure that the denominator does not have an imaginary part. If it has, then the answer, then you have not yet got the answer. So what you do, you have to rationalize just like we did here. That was question 1. Now question 2 came from UNEB 1994, paper 1, question 4a, and says, given that z is equal to 3 plus 4i, find the value of the expression z plus 25 over z. So you first write the given expression and then substitute for z. So where there is z, you put there 3 plus 4i, 3 plus 4i there. Now like I've told you, the denominator must not have an imaginary part. So what you do, you have to multiply up and down by the complex conjugate of the denominator, just like we did here. Now from there we shall simplify. This denominator is difference of two squares, so it will give you 3 squared which is 9, and 4 squared which is 16. Now now for difference of two squares in complex numbers we use plus here, because this one, when I square I, it will give me I squared which is negative 1. It will cancel with the negative which would have been here, that's why we have positive. So you must be confident with that in complex numbers. Rationalize difference of two squares, it gives you a plus, and the I goes away. Now from there, this is 25, and also this 9 plus 16 is 25, so meaning that they can cancel, remain with only 3 minus 4i. Then this one is also still maintained here. After that we shall collect like terms. This plus this gives you 6, and then this minus this gives you 0. So this is purely real. Then question 3 came from UNEB 1991, paper 1, question 6a, and says the total impedance Z of an electric circuit with branches Z1 and Z2 is given by this expression. Given that Z1 is equal to 3 plus 4i and Z2 is equal to 5 plus 5i, where I is square root of negative 1, calculate the total impedance Z in the form A plus BI. So here the good thing, we have Z1 and Z2, so we shall substitute for Z1 and also for Z2. Then from there we shall get LCM. So LCM of this and this will be the product of the two, which is this. Then from there we shall say this, the whole of this product divided by this. It will realize that 3 plus 4i cancels, remaining with 5 plus 5i, and 5 plus 5i times 1 gives you 5 plus 5i. Then also similarly, when I divide this by this, this cancels, remain with only this. So this times 1 gives you 3 plus 4i. Now next is to collect like terms in the numerator. This plus this is 8, this plus this is 9i. Then for the denominator, you open brackets, so you multiply. So when I multiply this by this, I'll come up with the whole of this. And next is to simplify. So collect like terms, this and this gives you negative 5, and this with this gives you positive 35i. But remember, this is 1 over z, but the question wants z. So what we do, we have to get the reciprocal. So z will be the reciprocal of this, which becomes now what was the denominator becomes the numerator, and what was the numerator becomes the denominator. Now we can't stop here because the denominator has an imaginary part. So what we do, to remove the imaginary part, we have to multiply up and down by the complex conjugate. So the conjugate of the denominator is 8 minus 9i, because this is plus, the conjugate will have minus. So when I multiply up and down, I'll open brackets for the numerator to come up with this. Then for the denominator, it will be difference of 2 squares. This squared to give you 64, and 9 squared to give you 81. So note that we are using plus here because we are dealing with complex numbers. Next is simplify further. This one gives you this, and this gives you that. So I can split the two because they wanted it in the form a plus bi. So you have to split the real part alone and also the imaginary part alone. And that's what they wanted. So now we shall go to question 4. Question 4 came from UNEB 2002, paper 1, question 13b, and says, find the sum of the first 10 terms of the series 1 plus 2i minus 4 minus 8i plus 16 plus dash 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 in the form a plus bi, where a and b are constants and I is square root of -1. Now this one is under series. I think we already covered the topic of series in this platform, so I believe this question will not be a little hard, will not be complicated. So this series is a GP with first term of a and common ratio of this. Because how do you know that's a GP? GPs must have a common ratio. So when I say this divided by this, I'll come up with 2i, and also this divided by this, I'll come up with 2i, because for example, if I have 4 over 2i, I'll remember that the denominator must never have a complex conjugate, must never have an imaginary part. So what I do, I multiply up and down by the complex conjugate. So multiply up and down by the conjugate of -2i, and also here times -2i. So when I do that, what will happen? It means that this one will give me -4i squared, which will be +4, and that +4 will cancel with this 4 to remain with only 2i, which is similar to this. So that means that this series has a common ratio, which means that it's a GP. So that's how to test whether the series is a GP or an AP. But more about APs and GPs is available on this platform. Just go in the folder for algebra and you'll see that topic there. So now that we have known that's a GP, we have to write the formula for the sum of the first n terms of a GP. But remember here they say the number of terms is 10, so they want S10. So S10 means that where there is n, you put there 10. Here we shall put there 10. And R, we have got it as 2i, so where there is R, we are going to put there 2i, 2i. And the first term we said it is 1, so where there is a, we shall put there 1. Now from there we shall use the calculator. When I use the calculator, the whole of this will give me this. Now how do I know that's positive? Because, so to use the calculator, let's first talk about that. So to use the calculator, I'll first ignore the I, and I'll deal with only 2. So 2 to the power 10 will give me 1024. Then what about the I? So I to power 10, how do I deal with it? I'll first pull the 2 inside and becomes I squared to power, now to be to power 5, because the 2 has gone out, has gone inside. Then from there, remember that I squared is -1, so I'll come and say -1 to power 5. So when I use a calculator, -1 power 5 gives me +1. Sorry, it gives me -1. So that is why here it was minus and here it is now plus. Okay, so now that we have known that, we shall go ahead. So here I cannot stop here because the denominator has an imaginary part. So when it has an imaginary part, the next thing to do is to rationalize or multiply up and down by the complex conjugate of the denominator. That's what I did here. So after that, I'll have to open brackets and simplify. So this one is difference of 2 squares, so it will be 1 plus 2 squared, which is 4. Remember, for complex numbers here it has to be plus, not minus. Now this is 5. Now the whole of this 1025 divided by 5 gives me 205. Then from there I'll multiply this with this to give you this, and also this with this to give you that. And that's what they wanted. So that has been arithmetics of complex numbers. We have seen how to add, how to multiply, how to divide, and how to subtract. Now we shall go to the next part, which is complex roots of equations with real coefficients. Now, I think you remember under the topic of quadratics and polynomials, we saw that sometimes the discriminant can have complex roots, but we never talked much about complex roots. So now in this video we shall talk about that part. So previously what we would do, we would just say x is undefined, but now we shall talk more about the complex roots. So the complex roots of a quadratic equation this can be got using the quadratic formula this, just like we did under quadratics and polynomials. So the video on quadratics and polynomials is also available on this platform under the section of algebra. So with that, let's go through the questions. So question 1 came from UNEB 1988, paper 1, question 4b, and says solve z squared plus 4z plus 13 equal to 0. So here we shall use Bulldozer. So here we cannot use factorization under complex numbers. You have to use Bulldozer, it's the only option. So Bulldozer methods is this, the Bulldozer method or quadratic formula, and this is a is now 1. That's why you put 1 here and also 1 there. Then b is 4, that's why you put here -4, and also here we put 4 squared. Then c is 13, that's why you put here 13. Then from there we shall simplify. This in bracket is -36, and previously when we reach here we'll just say that x is z is undefined, but now we don't stop there. What we do, we shall remember that -36 is the same as -1 times 36, so that's why it's split to give you square root of 36 times square root of -1. Now from there I'll remember that square root of -1 is I, that's why I put I here. Then square root of 36 is 6, that's why I put 6 there. After that, next is to simplify. This 2 can divide this to give you -2, and this 2 can divide through this to give you +3. That is why, so the answer will be -3 plus or minus 3i. So those will be the roots or complex roots of this quadratic equation. Then question 2 came from, so question 2 says solve this quadratic equation. So we shall go through the same procedure. We shall use the quadratic formula, or what we call the Bulldozer method. So substitute for b here and here, substitute for a here and here, and substitute for c here. Then use the calculator to simplify. Now from here I'll realize that this 12 is the same as negative 12 is the same as 4 times negative 3, so the 4 can come out to become 2. Square root of 4 is 2. Then inside I have only negative 3. Now negative 3 is the same as 3 times square root of 3 times square root of negative 1. And this 2 has cancelled because this 2 cancels with this to give you negative 1, and also it cancels with this to just remain with this square root of negative 3, which is the whole of this. Now from there I realize that square root of negative 1 is I, so I'll put I there, and that will be the answer. So from here there's something we need to conclude, is that based on the roots got, it can be concluded that if a complex number is a root to a given quadratic equation or to a given equation, even its complex conjugate is automatically a root. So that one is going to push us to what we are going to cover in the next part of this video. So but remember that when a complex number is a root, then its conjugate is also a root. So that was question 2. That was quadratic equations. What about cubic equations? So question 3 came from UNEB 2003 paper 1 question 12b and says solve the equation z cubed plus 1 equal to 0. So here this is cubic, so what we are going to do is first let fz to be this function, because here we have to first look for at least one of the roots. So one of the root is negative 1. So when I put z equal negative 1, I realize that I come up with 0, which is here. That means that z equal negative 1 is a root, and therefore z plus 1 is a factor. So now that I've got at least one of the factors, I'm going to do long division to divide this cubic equation by this factor to be able to get the other roots. So dividing, I'll say this factor I'll put it here, and this function I'll put it here. So I'm putting these zeros to ease the division. So what I'm going to do, I'll come and say, remember, divide highest power, highest degree with the highest degree. So z cubed divided by z will give you z squared, so I'll put it here. That's the first thing. Then next is to multiply this z squared throughout the whole of this to give you this. Now after that, next will be to subtract the 2. So when I subtract, I'll come up with that. Then I'll do the same, repeat the procedure, this divided by this, I'll come up with negative z. Now negative z multiplied throughout by the whole of this will give me this. After that, I'm going to subtract the 2 to come up with 0. So this is this minus this is 0, and this minus this, so this minus this, I'll come up with z, because this is 0 minus negative 1 to give you positive z. Then 1 minus 0 to give you 1. Then I'll do the same still, this divided by this to give you 1. Then this one multiplied throughout by this will give you that. Then next is subtract the 2, and when I subtract the 2, I'll come up with 0, meaning that there's no remainder. And there's no remainder because this was a factor. If it was not a factor, there would have been a remainder here. So what does that mean? It means that this cubic equation here can be written as a product of this factor with this quotient. So now either this is equal to 0 or this is equal to 0. So for this equal to 0, I'll come up with z equal to negative 1, which you already know. But now this one, you don't know the roots yet. So since the quadratic, we need to use the bulldozer method. So you come and say that for this quadratic equation, you're going to use the bulldozer method, or what you call the quadratic formula, to come up with this as the roots of z. Therefore, we shall conclude that the roots are this, this, and this. Remember, it was cubic, meaning that it must have 3 roots. Okay, so that was cubic, but a little simplified. Let's go to this one, which is question 4, says solve for z. So this should be z. Solve for z in this cubic equation. So still we shall go through the same procedure. We shall let fz be equal to this expression. Then we shall look for a root or a value which satisfies this equation, and to be 1. So when I put 1, I'll come up with 0. That means that z equal to 1 is a root, therefore the factor will be z minus 1. So by long division, still I do the same. I'll go through the same procedure, put here the divisor and put this function here. Then I'll start. This z should divide by z to give you z squared. Then z squared multiplied through the whole of this gives you this part. Then subtract the 2, you'll come up with this. So this cancels, you remain with this minus this gives you this gives that, this gives you that. Then do the same, this divided by this gives you negative 6z. Then negative 6z divided by the whole, so multiply through the whole of this gives you this line. Then subtract the 2, you'll come up with that. So still the same, 13z divided by z gives you positive 13. Then 13 multiplied through the whole of this gives you that. Then subtract the 2, you'll come up with 0, meaning there is no remainder. Therefore this is also this, meaning that this is a factor. Therefore shall come and say that writing this here, it is the same as writing this factor by this quotient. So either this is equal to 0 to give z equal to 1, and this is equal to that. So for this quadratic we need the roots, so we shall come and isolate it out and then use Bulldozer method to come up with the root. Therefore the roots, we shall conclude that the roots are this, this and that. So that has been complex roots for equations with real coefficients. Now we shall go to the next part, which is formation of quadratic equations given the complex roots. So you already know that if a complex number is a root to a given equation, even its complex conjugate is also a root. I think you remember that conclusion we made when we are getting the roots for quadratic equations. So this is that conclusion we made will work for this part, formation of quadratic equations given complex roots. So sometimes they can give you only one complex root to imply that even its conjugate will be a root. Now the quadratic equation in Z whose two roots are unknown. So now that when you know two roots, then you can get the quadratic equation by using the formula, which is z squared minus sum of roots multiplied by z plus product of roots equal to 0. So this equation is also familiar because you already dealt with it under quadratics and polynomials still under algebra, and that video is also under this, is also available on this platform. So there's nothing more to write, let's just go to the questions. But if you need more on this, you can go and revisit that video. So question 1 came from UNEB 2002 paper 1 question 13a and says find the equation whose roots are -1 plus or minus I, where I is in the square root of -1. So I think you realize that even here they have given you a complex number and its conjugate. So always if a complex number is a root, even its conjugate has to be a root. So here they have simplified it by giving you both the complex and its conjugate. So you come and say the sum of roots. So sum of these two roots will give you -2, because if you look at this I, this minus this gives you 0. So you only remain with this and this, which is -2. What about product? Product of roots will be difference of two squares. So this squared is this plus this squared, which is that. I think by now you know why here it is plus and not minus. So when I add the two, I'll come up with this. So I've got the sum and product. Next is to quote the required equation. So I know that it will be good from here. I'll substitute for sum here and also substitute for product here. So when I do that, I'm going to come up with this expression. Then this negative and this negative will become positive, so we'll end up with this as the required quadratic equation. Then question 2 came from UNEB 2011 paper 1 question 10a and says form a quadratic equation having this as one of its root. Now here in question 1 they gave you both roots, complex and its conjugate, but now here they're giving you only one root. So you have to remember that if this is a root, then its conjugate must also be a root. So now that we have two roots, we can easily get the equation. Therefore, sum of roots will be this. When I add the 2, I'll come up with this. When I multiply the 2, I'll come up with 25. Therefore, I'll come and quote the general formula for general expression for the quadratic equation and substitute for sum and product, and that will be the answer. Now we shall go to showing that a root, showing that a complex number is a root to a given equation. So previously we saw how to get complex roots of quadratic equations or cubic equations, but now here in this topic what they do, they'll give you a cubic equation or quadratic equation, and they give you and they tell you to show that a given root is a root to that cubic equation. So there, when they do that, you have to go through these steps. Step 1 is form a quadratic equation using the given complex number and its conjugate, and that's what you have seen in the previous part. Then 2, use the method of long division to divide the given cubic or quadratic equation by the quadratic equation formed in step 1. I think we also saw that long division in this video earlier on. Then step 3 says if there is no remainder, it implies the given complex number is a root to the given cubic or quadratic equation, otherwise it is not. So you must do long division and ensure that the remainder is 0. So with that brief intro, we shall go through this question. So question 1 came from UNEB 2002 paper 1 question 3 and says show that this is a root of the equation this. So now this is the cubic equation, and hence find the other roots. So here we shall remember that if this is a root, then its conjugate must also be a root. So now that you have two roots, we shall be able to get the quadratic equation. So sum of roots is that product of roots will be this, therefore the quadratic equation can be stated. So you substitute for sum and for product to come up with that. Now after that, that is step 1, getting the quadratic equation. Step 2 is to do long division. So you come and say that by long division, I'll come and make this one the divisor, and this one will be the expression to be divided. So I would still do the same procedure. This divide by this, you'll come up with 2z. Then 2z multiplied by throughout the whole of this gives you this part. After that, next is to subtract the 2. So when I subtract the 2, I'll come up with that. Then still this and this I can divide. So the whole of this divided by this, I'll come up with -1. So this -1 multiplied throughout the whole of this gives you that expression. The next is to subtract. When I subtract the 2, I'll come up with 0 as the remainder. 0 meaning that there's no remainder, therefore we have shown that this is a root to this. But they also said for the hence part that get the other roots. So the other roots will be, we shall say that since there is no remainder, then this is a root of this equation. Now let's go and get the other roots. One of the other root we have already got it, the conjugate. Then the other one will be got from this here, the quotient. So for the hence part, this is the given equation, then it can be written in this form, divisor multiplied by the quotient. Therefore from this one, we already saw that these are the roots. Then from this, the root is that, and that's what they wanted. So the other roots will be this, because this one was already given. Then question 2 came from UNEB 1989 paper 1 question 8b and says show that z1, which is this, and z2, which is this, are the roots of the equation this, and hence find the other roots. So here they have helped us. They're giving us a complex number and its conjugate. So we shall do the same procedure. Step 1 is to get the quadratic equation. So sum of roots is that, product of roots will be this, and therefore the quadratic equation will be got from that. So substitute for sum and for product to come up with that. So next is to do long division. So by long division, this will be the divisor, and this will be this given equation function will be put here. So dividing this divided by this gives me z squared, which is here. Then z squared multiplied by this gives you that. And when I subtract the 2, I'll come up with this. Then I'll do the same. The whole of this divided by this gives you negative z. The negative z multiplied throughout the whole of this gives you that. Then I subtract the 2 to come up with this. Then do the same. The whole of this divided by this gives you positive 1. And positive 1 multiplied throughout the whole of this gives you that. Then I'll subtract the 2 to come up with no remainder. Therefore, since there is no remainder, it implies that this and this are the roots of this equation. So for the hence part, we shall come and say that this one, we're interested in this part, so this part will be a quadratic. I'll have to solve it using Bulldozer method to come up with these roots. Therefore, those will be the other roots, because we already have 2 roots. We are left with the other 2 to get the 4 roots of the quadratic equation, and these are the 2 roots which were remaining. So now we shall go to another part, which is called equality of complex numbers. Now here, there's something small we need to know. It says that for 2 complex numbers to be equal, it implies that their real parts will be equal and their imaginary parts will be equal. For example, if I have z1 is that and z2 is that, it implies that when they are equal, then this real part of A will be equal to this real part of z2, which gives you this part, and also the imaginary part of this z1 will be equal to the imaginary part of z2, and that gives you this part. That is the only thing you need to know. Now let's go to the questions. So question 1 came from UNEB 2009 paper 1 question 12A, and says, given that this is equal to that, find the values of x and y. So here we shall first write what is given, which is that. Then we can cross multiply. So this goes with this and this with this to give you this line. Then next we can open brackets. So when I open brackets for this, I'll come up with that. So by comparison, so here, remember we said real parts will be equal and imaginary parts will be equal on both sides. So even here, in this part, when I compare real parts, here there's no real part because the whole of it is imaginary. So this side it will be 0, but this side there will be 3, and there will also be negative 4y. So I come and say that if comparing real parts, 0 will be equal to 3 minus 4y, therefore y is 0.75 when I make it the subject. What about when I compare the imaginary? So imaginary part will be the whole of this being equal to this 3y plus 4. So that's this line. Then the good thing, I already know the value of y, so substitute for y here and here to remain with only x as the only unknown. So this is a quadratic. I'll solve it using Bulldozer method and come up with 2 values of x, this and that. And that's what they wanted. You have got the value of y and the corresponding values of x. So now we shall go to question 2. Question 2 came from UNEB 2006 paper 1 question 9b, and says, find the values of x and y in this expression. So still we shall do the same. Now that here, now on the left hand side there are 2 terms. So what we do, we shall first get the LCM. So when I get the LCM of this, I'll come up with LCM of this. It will be this times this, which is this, then this LCM divided by this, you realize this cancels, you remember this part, so this part times x gives you this part here. Then do the same, the whole of this LCM divided by this will cancel, you remain with this, so this times y gives you this expression. So the minus is maintained. This side I'm going to rationalize. So that means that I'll multiply both up and down by the conjugate of this, which is this here and this here. So next is to open brackets here. When I open brackets here, I'll come up with this, and also when I open brackets here, I'll come up with this. Then here when I open brackets, I'll come up with this, and open brackets here, difference of two squares gives you that. Simplifying will give me this. Then from there I'm going to cross multiply. This by this gives you this part, and this by this gives you this part. Then I'm going to open brackets here to come up with this side, and here I'm going to split the two, real part alone and imaginary part alone. Then here also I can get the real part, which is this and this, and imaginary part, which is this and this. So let's see that in the next slide. So this is the real part, this is the imaginary part when I collect like terms. Therefore I'm going to compare because they are equal. So comparing real part means that this one is equal to this. So I'll come and write that. This, then I divide this 64 goes this side. So 494 divided by 64, 65 gives you 7.2, and that is equation 1. Then do the same for the imaginary part. The whole of this with this negative is equal to the whole of this with this negative. So divide this divided by this coming this side gives you that. So those are two equations and two unknowns, so we can solve them simultaneously. Therefore I come and say that equation 1 multiplied by 2 minus equation 2 multiplied by 3 gives you this. So when I multiply 2 throughout this gives you that, multiply 3 throughout this gives you this. Now I'm going to subtract the 2. When I subtract the 2, x will be eliminated and remain with this. Therefore I can make y the subject. Now that I have y, I can go to either equation 1 or equation 2. So when I go in equation 1, I will substitute for y, and then be able to get the value of x. And those are the two values they wanted. Then question 3 came from UNEB 2017 paper 1 question 9a and says, given that the complex number z and its conjugate z bar satisfy the equation this, find the possible values of z. So yeah, what we are going to do, we are going to first let z to be equal to x plus yi. You can let it to be a plus bi if you want, there's no problem. That means that the conjugate will be x minus yi. Therefore I'll come and code this expression given, then substitute for z and for z bar. Then from there I'll have to expand. So when I expand, this, the difference of two squares gives you this, and this one gives you, that one gives you this, then this one gives you this. Next is to collect like terms, and to collect like terms I'll come up with this. Then from there I'll have to compare. So comparing imaginary part implies that this side there is negative 4y and here there is negative 4. So negative 4y equal negative 4 gives you y as 1. What about when I compare real parts? I'll have here this side should be this and this side should be 5. So x squared plus y squared equal to 5. Substitute for y and be able to get the value of x as plus or minus 2. Now they didn't tell you to get x and y, they told you to get z. So in the end I'll have to remember that z is equal to x plus yi. So I'll come and substitute for x and also substitute for y, and that's what they wanted. Then question 4 came from UNEB 2014 paper 1 question 9a and says, given the complex number z and its conjugate z bar satisfy this equation, find z. So I'll do the same, substitute, let x z be equal to this, s conjugate will be that, therefore substitute for z and z bar to come up with that, then expand to come up with that, then you can compare. So comparing imaginary part, there is this negative 2x equal to 6, therefore x is negative 3. What about when I compare real parts? Real parts, there is this, there is this, there is this equal to this. So I'll come up with that equation, substitute for x, simplify, I'll get a quadratic in y, therefore use Bulldozer method to come up with the two values of y, and therefore z will be this, or z is equal to that, and that's what they wanted. So that has been equality of complex numbers. Now we shall go to the next part, which is the Argand diagram of a complex number. So this is a graphical representation. Now I'm saying graphical representation, this does not mean that you need a graph paper. It is only a sketch. Remember, math paper 1, we only make sketches, we don't need graph papers. So this is a graphical representation of complex numbers, and it shows the real part, imaginary part, modulus, and argument of the complex number. The horizontal axis is known as the real axis and denoted by z to mean real z, while the vertical axis is known as the imaginary axis and it's denoted as mz. So this is mz. So we no longer say x-axis or y-axis, we shall use z and mz for this Argan diagram. Now we have talked about the modulus and argument. So what are these ones? So the good thing, we already know what real means and what imaginary means, but these two we don't know them yet. So modulus, if it was vectors, modulus would mean magnitude of a vector. So in the same way, modulus of a complex number means magnitude of a complex number. Then argument, if it was vectors, it would mean the direction of the vector or the angle it makes with the horizontal. So here still, argument of a complex number is the angle measured from the positive real axis up to the given complex number. So the argument of a complex number, we have seen there's an angle, but that angle is restricted to a certain range. So it ranges from negative 180 degrees to positive 180 degrees and can be measured in radians or degrees. So this one is in degrees. If it is in radians, it will be from negative pi to positive pi. And the word argan, or the argan, is noted by arg z. So the argument of a complex number z is noted by arg z. So when you see this arg z, it means they want argument. So now let's see how we can get the formula for getting modulus and argument of a complex number. So since positive angles are measured in an anti-clockwise direction, I think remember that under trigonometry, it implies the complex numbers which lie in the first and second quadrants have positive arguments as shown below. So for example, like I told you, positive angles are measured from here going in this direction, and negative angles are measured from there going in this direction. But now since the argument ranges from negative 180 degrees to positive 180 degrees, meaning that it means that positive 180 degrees will stop here and cannot exceed, meaning that positive arguments will lie either in the first quadrant or second quadrant, and negative arguments will lie either in the third quadrant or fourth quadrant. So we shall see all these four cases. Let's start with the first case, or the first quadrant. So for the first quadrant, the complex number will lie in this part. In other words, the real part will be positive and the imaginary part will be positive. So that means that it will be, this is the real part A and the imaginary part is B. Therefore it will give you A plus BI. And this will be the argument of Z1. So argument will be equal to arctan B over A, because this is the This is the opposite. Based on this is the opposite, and this is the adjacent. Therefore, tan this angle will be equal to opposite over adjacent, which is b over a, and to be arctan. Therefore, the angle will be arctan that ratio. So that, what does that mean? It means that it is a rule that always the argument or the angle will be arctan of the imaginary part over the real part. This is the imaginary part and this is the real part. So always remember that the numerator will be the imaginary part, denominator will be the real part. And this angle is positive because it is an anti-clockwise direction. What about modulus? Modulus is magnitude, therefore to be given by square root of this squared plus this squared, everything under root, and that would be the magnitude or modulus. So in complex numbers we stick to the word modulus. That has been first quadrant. What about the second quadrant? Second quadrant, it means that the real part will be negative. Therefore, you shall put here negative a, but the imaginary part will be positive. Therefore, the complex number will be that negative a plus bi, and the argument will be that. But for you to get this argument, you have to first get this angle. So let's first call it theta 2. Now here, that means that arg of z2 or argument of z2 will be equal to 180 minus theta 2, because the whole of this from here to here is 180 and this one alone is theta 2. Therefore the remaining part will be the argument which they want. It will be 180 minus theta 2. So the question is, how do we get theta 2? Theta 2 is got by arctan of b over a, because b is the imaginary and a is the real. But realize that here there is a negative. So what we do, in order not to confuse you, we are going to put a magnitude symbol, because our interest is not in this negative. The negative only tells us the quadrant where it lies. But because we don't want to get confused along the way, let's put this magnitude sign. So this magnitude sign means that whatever is negative becomes positive. Because if you just put here positive a, someone may wonder, why do we put positive a yet here it is a negative a? So in order to avoid those questions, let's put this magnitude signs. Each time you get a negative anywhere, remember to put this magnitude sign. So this will be the argument for a complex number in the second quadrant. You must be keen with them, because for modulus it is easier because it is just square, but for argument you must be keen. First quadrant it is just arctan b over a, or arctan real, imaginary over real. But for second quadrant is 180 degrees minus arctan of imaginary over real in magnitude. We shall see how these ones are applied, but let's first look at all the four cases. So the third case will be for the third and fourth quadrant, because those ones are in the third and fourth quadrant. They have negative arguments. That's one thing you need to first remember. So for the third quadrant, it implies that both are negative. The imaginary part is negative and is here, and the real part is negative, and also the imaginary part is negative. Therefore the complex number will be in that form, negative a minus bi. So when you see this, when you see both the imaginary and real are negative, just know that the complex number lies in the third quadrant, and the argument will be in this direction. Now this direction means it is negative because it is clockwise. But for you to get it, you need to first get this angle. So let's first call it theta 3. Therefore you come and say that argument of z3 will be equal to negative. Why are we saying negative? Negative because it is going in an anti-clockwise direction. Negative of what? Negative of 180 minus theta 3, because the whole of this is 180 and this one is theta 3, so the remaining part will be 180 minus theta 3. So I believe you know why we're putting this negative. It is because of the direction. Now when I open brackets, I'll get theta 3 minus 180 degrees. Then I substitute for theta 3. Theta 3 will be arctan of imaginary over real. Like I said, each time you get a negative somewhere, remember to put the magnitude symbol so that you don't get confused along the way. So this is the argument for third quadrant. The modulus is easier because you have square and everything under square root, but argument is what disturbs most students. So remember, for second quadrant it was 180 minus arctan. Third quadrant it is arctan minus 180. What about the fourth quadrant? So fourth quadrant, it means that the real is positive and imaginary is negative. So shall put real here positive and imaginary here negative. So when I draw the complex number, it will be in that form. And the argument will be this. It is clockwise. Therefore, in this case, the argument will just be got by arctan, negative of arctan, imaginary over real. Now we are putting magnitude symbol because this imaginary part has a negative. So each time there's a negative somewhere, remember to put this magnitude symbol so that this negative does not disturb you along the way, as we shall see when we are dealing with worked examples. The modulus is easier, only that here I forgot to put this. You have to put them there. These symbols are very vital, you have to put them there. Okay, so this one is somehow related to the first quadrant. First quadrant was positive arctan, then fourth quadrant it is negative arctan. Second quadrant it was 180 minus arctan. Third quadrant it is arctan minus 180. So there is some bit of relationship. Okay, so now that you have seen how to get argument and modulus, let's go to the questions and apply those formulae. So question 1 says, represent each of the following complex numbers on an Argan diagram and hence find their modulus and argument. So look at this first one. Both are positive. Positive real, positive imaginary. Therefore we shall come and draw, locate our positive 2. Remember we said here we just sketch. So locate positive 2 here and locate positive 3 here. Then the line from the origin to this point will be your complex number. Remember to put this arrow at the end. So this is what they call the Argand diagram, a representation of a complex number on the real and imaginary axis. But they also told us to get the modulus and argument. So modulus, it is easier, this squared plus this squared, everything under square root, to come up with this modulus. But argument, you must be keen. So imaginary part is 3, so imaginary over real, and that will be this. So angles are rounded off to 2 decimal places. So it will be 56.31. That was Roman 1. Roman 2, they want for negative 2 plus 5i. So negative real and positive imaginary. So we shall put here negative 2 and put here positive 5. Then the complex number will be from the origin to this part, and that's what they wanted. So the argument, this is the argument, but to get it you have to first get this angle. Then we shall come and say that modulus is this squared real squared plus imaginary squared, everything under square root, to give you a square root of 29. The argument is 180. Remember we said this is second quadrant. Second quadrant is 180 minus arctan. Now because there's a negative somewhere, that is why we put this magnitude symbol. Now what do those magnitude symbol mean? It means that what is negative becomes positive. So in your calculator, when you're pressing, instead of pressing 5 over negative 2, you are going to press 5 over 2 because the negative has gone away. and arctan of that will give you this. Therefore, when I subtract the 2, I'll come up with this as the argument. So now we shall go to Roman 3. Roman 3, it was negative 3 minus 4i, meaning that both are negative, implying that they are in the third quadrant. So we shall show negative 3 and also negative 4 here, and this will be the complex number. Remember to put the arrow. So from there you can get the modulus easily. This squared plus this squared, everything under square root. That one is easy, but the argument is where you must be careful. So here for the third quadrant, argument is arctan minus 180 degrees. But because there's a negative somewhere, that is why we are putting this magnitude symbol. So magnitude symbol means that on your calculator, instead of pressing negative 4 over negative 3, you are going to press 4 over 3 here. And you'll come, and arctan of that will give you this. Therefore, and then you come up with this as the argument. So now we shall go to Roman 4. Roman 4 is 2 minus 3i. So positive real and negative imaginary, meaning it's in the fourth quadrant. So we shall put positive 2 here and negative 3 here. And this will be the complex number. The arrow has to be seen. So modulus is easy. Real squared plus this squared, everything under square root to give you that. But argument, you must be keen. It is now negative arctan. So if it is in the fourth quadrant, it should be negative arctan. And because there's a negative somewhere, that is why we are putting this magnitude symbol. So in your calculator, instead of pressing negative 3 over 2, you are going to press 3 over 2. So that's what this magnitude means. Always remember that. So this one alone will give you positive, then this negative will cater for this. So question 1 was briefly introducing us to modulus, argument, and how to draw the argand. So now we shall go to UNEB questions. So question 2 came from UNEB 2011 paper 1 question 10b and says, given that z1 is this and z2 is that, express z1 over z2 in the form this, where a and b are real numbers. Then Roman 2 represents z1 over z2 on an Argan diagram, and Roman 3 get the modulus of z1 over z2. So this is division. I think remember how to divide complex numbers. So that's the same knowledge we're going to use. Here, because there is an imaginary part here, we have to rationalize by multiplying up and down by the complex conjugate of the denominator, which is this. Do it on the denominator and also on the numerator. Then expand this and this gives you this, and this with this different of 2 squares gives you this. So in the end, we shall come up with this as the complex number of z1 over z2, and that's what they wanted in Roman 1. Then Roman 2, they wanted to represent it on an Argan diagram. So negative real, and also negative imaginary, meaning it's in the third quadrant. So let's do that in the next slide. So negative real, negative imaginary, therefore the complex number will be in the third quadrant. Then they also wanted its modulus. So modulus is easier. This squared plus this squared, everything under square root, to give you 1 as the modulus they wanted. Then question 3 came from UNEB of November 1998. Paper 1 question 9a and says, given that z1 is that, z2 is that, and z3 is that, represent this, this, and this on an Argan diagram. Also show the representation of this. So first of all, you have to first get those 3. We have to first get these products. So this, I think, remember how to multiply 2 complex numbers. So this and this, multiply the 2 will come up with this complex number. What about when you subtract? I think you also remember how to subtract. You come up with 3. What about dividing? I think you remember we said for the denominator it must never have an imaginary part. So here we have to rationalize by multiplying up and down by the conjugate to come up with this as the complex number. So they also wanted us to show this representation, so I'm going to substitute. We know that this product, it was already got here, so that's what you're going to put here. Then this denominator here, subtraction, was already got here, so that's what you're going to put here. Then 1 over z was already got here, which is this, so that's what you're going to put there. The next is to get LCM. LCM is 6, so 6 divided by this is 2. 2 times this gives you this part. Then also 6 divided by 2 is 3. 3 times this gives you this part. So next is to open brackets and collect like terms, then come up with the complex number. So now I've got all these complex numbers. I've got this, and this in terms of a plus bi. Therefore, I can now represent them on the Argand diagram. Remember, we only make a sketch. We don't use a graph paper. So, and we only show the necessary parts, the necessary points. So for the horizontal, we shall show all those points because they are needed, and for the vertical, we shall show those points because they are needed. So let's start with the first one, complex number, and that will be the product z2 z1. Then the second one was this difference, z2 minus z1, which is that. Then the other one was the reciprocal, which is 1 over z1, and the last one was the one which was combined, and it was that. So basically that is what they wanted. So now we shall go to arithmetics of modulus and argument of two complex numbers. So what you have seen previously has been getting modulus and argument for each complex number, but they can combine two complex numbers and they tell you to get their modulus or argument. So here we shall consider two complex numbers, z1 and z2, whose moduli are this one is the modulus for complex number z1, and this will be the modulus for complex number z2. Then this will be the argument of complex number z1, and this is the argument of complex number z2. So by now I believe you know how to get the moduli and the arguments. So it implies that for division we have a special way of dividing, getting the modulus of division. So if I say z1 over z2 and they want their modulus, I'll just get the modulus of z1 alone, put it here, then over the modulus of z2 and put it here. So for modulus of division is the same as individual moduli when they are divided. But when it comes to argument, it is somewhat different, because for argument it is subtraction. So if it is division here, it means you have to subtract. What is the numerator is the one which starts, and denominator is the one which goes last. It's somehow like logarithm. I think you know that log of a over b is the same as log a minus log b. So argument, take it like as if it is a logarithm. That's how you can easily remember the concept. What about for multiplication? For multiplication, argument of the two products the same as the individual product of both modulus. So modulus of the product the same as the individual moduli when they are multiplied. So modulus of z1 z2 the same as modulus of z1 times modulus of z2. But when it comes to argument, just like it is in logarithm, log of a b is the same as log a plus log b. So in the same case also, argument of z1 z2 is the same as argument of z1 plus argument of z2. Furthermore, they can also give you powers. So z1 raised to the power n, the modulus of z1 raised to the power n is the same as modulus of z1 alone, then you raise to the power n. Then for argument, just like it is in logarithm, for example, log a to power n the same as a log n log a. So even here, argument of z1 to raise the power n the same as n times argument of z1. So those are the three basic concepts when we are dealing with modulus and argument of two complex numbers. So let's look at the examples from UNEB and see how those concepts can be used. So question 1 came from UNEB 2019 paper 1 question 9 and says show that the modulus of this is equal to this. Now I think you see that now the concept we have learned is going to help us, because if you look at this one, if you want to first expand it, expanding a power of 6 will be a bit longer. So there what we do, we just use the concept we have learned and say that modulus of this, first of all, modulus of a division the same as modulus of this alone over modulus of this alone, which is here. Then after that we shall remember that modulus of anything raised to a certain power the same as modulus of this one alone. After that you bring the power outside. So that one becomes simpler because this one I can easily get its modulus, which will be 1 squared plus negative 1 squared. Now remember to use the bracket. Then this one also 1 squared plus 1 squared. So for modulus we don't include the I. I think you have realized that. The I is there to show that this is an imaginary part. So next is to use the calculator. So first of all, this one alone is root 2 and this one is also root 2. So same base to divide the power. Same base, it means that you subtract the power. So that is just rule of indices now. So this is the same as root 2 to power 1. So it means that it becomes root 2 to power 6 minus 1. So then you come up with root 2 to power 5. But the one to show that it's equal to 4 root 2. So root 2 to power 4 is equal to 4. Then times root 2, that's because this one to power 5 is the same as root 2 5 times. So this is root 2, then also root 2 5 times. This one gives you 2. Then do the same, root 2, another root 2 gives you another 2, that is 4. Then there is one remaining, which is root 2. So in the end you come up with 4 root 2. Now shall go to question 2, which came from UNEB 1996 paper 1 question 10a and says given that z is equal to this, find the modulus and argument of z squared, then 1 over z, then Roman 3, show on an Argan diagram the points representing the complex numbers z, z squared, and 1 over z. So you first get the modulus and argument of only z. So this one modulus is this squared plus this squared, everything under square root to give you 2. Then the argument, all are positive, so just say arctan 1 over root 3 to give you 30 degrees. So now shall go to Roman 1. Roman 1 you have to get the modulus and argument. So when you start with the argument, so argument of z squared is the same as 2 times argument of z. You already got argument of z here, so shall just come here and say 2 times 30, which gives you 60 degrees. Remember we said argument can be given in degrees or radians. If you want radians, then you have to convert the degrees to radians by saying 60 times pi over 180. But for our case, let's just leave it in degrees. So modulus still, modulus of z squared is the same as modulus of z, everything raised to the power 2. And modulus of z was 2, so raising to the power 2 gives you 4. That was Roman 1. Roman 2, they want modulus and argument of 1 over z. So you come here and say that argument of 1 over z is the same as argument of z to power negative 1, which becomes negative 1 times argument of z. So here I'll write negative 1 times 30, which gives you negative 30 degrees. They also wanted the modulus. The modulus of 1 over z is the same as 1 over modulus of z, which gives 1 over 2, and that's the answer. Then now shall go to Roman 3. So Roman 3 says show in an Argan diagram the points representing complex numbers z, z squared, and 1 over z. So here we have got argument and modulus. So that's what we shall use to locate our complex numbers. So previously we have been using real part and imaginary part, which is also okay, but in this case, since we have only modulus and argument, that is what we are going to be using to locate our complex numbers. So you have to remember that a positive argument starts from the horizontal and going in an anti-clockwise direction. So for example, z, if you look at z, the argument was positive 30. So from here going in anti-clockwise, we measure 30 degrees. That's where it is. Then it was 2 units. The modulus was 2. So you have to measure a length of 2 units. And that is it. Like I told you, this is a sketch. You don't need to be accurate. So that is z. What about z squared? Z squared will be that the argument was positive. So it will be that, and the modulus was 4. The next is 1 over z. So 1 over z, the argument was negative 30, that's why it is in a clockwise direction, and the modulus was a half, which is there. And now we shall go to question 3, which came from UNEB 1989, paper 1, question 8a, and says, given that z1 is this, z2 is this, find the modulus and argument of this and that. So let's start with the Roman 1. So first of all, we shall remember that this is the same as modulus of z1 alone raised to the power 2 times modulus of z2 alone raised to the power 2. So modulus of z1 is this one in brackets, but remember it is raised to the power 2. Modulus of z2 is this one in brackets, but remember it is raised to the power 2. So in the end we shall come up with 100 as the required modulus. But they also wanted the argument. So argument of this is the same as 2. Everything is raised to the power 2, so we can pull up the 2 at once. In brackets you say argument of z1 plus argument of z2. We are saying plus because it is a multiplication here. Then we substitute for argument of z1. Remember, argument of z1, if you look at this z1, it is in the 4th quadrant because real is positive but imaginary is negative, meaning it is in the 4th quadrant. And in the 4th quadrant, remember we said argument is negative arctan. And we also said that as long as you see any negative somewhere, you have to put it in brackets. That's why this one is you have to put it in magnitude. That's why here there are vertical lines to mean magnitude, but here they are just curved brackets because here everything is positive. So always remember that if there is any negative somewhere, you have to put magnitude sign so that you can eliminate the negative. So what does that mean? It means that when you're pressing your calculator, instead of pressing negative 1 over 3, you are going to press 1 over 3, because magnitude means that what is negative becomes positive. Therefore in the end we shall come up with this and this. Now this negative is because of this, so it is maintained, and this negative and positive gives you 0, so the argument is 0 degrees. That was Roman 1. Roman 2, they want z1 over z2 modulus and argument of z2 over z1. So let's start with the modulus. Modulus of z2 over z1 is the same as modulus of z2 over modulus of z1. So modulus of z2 is this, modulus of z1 is that. And then you come up with 1. What about argument? Argument of z2 over z1 is the same as argument of z2 minus argument of z1. Then you substitute. So you must be keen with the brackets. Here we use brackets because of this negative here. We don't want it to be disturbed with this one. So in the end, this and this gives you positive. That's why you see plus here. And I believe by now you know why we put magnitude sign on this case, because of this negative. In the end, we shall come up with this as our argument. Now we shall go to question 4, which came from UNEB 1995, paper 1, question 4a, and says Roman 1, express each of the complex numbers z1, which is that, z2, which is that, and z3, which is that, in the form this, where a and b are real numbers. Then part b, or Roman 2, find the modulus and argument of z1, z2, z3, the product, given in I above, in Roman 1 above. So let's start with Roman 1. Roman 1, this one we have to expand until and then simplify to come up with this. Then Roman 2, the denominator has an imaginary part, so you have to rationalize. In the end we shall come up with this. Then Z3 also, the denominator has an imaginary part, so you have to rationalize, and in the end we shall come up with this. So we have got Z1, Z2 and Z3 in this form A plus BI, which they wanted in Roman 1. Now when we come to Roman 2, they wanted modulus and argument of Z1, Z2, Z3, the product. So I show that this modulus is the same as modulus of Z1 times modulus of Z2 times modulus of Z3. So you substitute modulus of Z1 is that, Z2 is that, Z3 is that. Simplify, you come up with that. In the end you come up with this as the required modulus. Then the argument of this the same as argument of Z1 plus argument of Z2 plus argument of Z3. Substitute, this is arctan 1 over 3. Then this one is 90 because it is entirely imaginary. So from here to here to be 90 degrees. Then this one, it is that, I think by now you know why we put this magnitude sign. So we use the calculator to come up with that, and in the end we shall come up with this as the required argument. Then question 5 came from UNEB 1988, paper 1, question 4a, and says, given that Z1 is that, Z2 is that, find modulus of Z1 over Z2, and Roman 2, modulus and argument of the whole of this. So for Roman 1, modulus of this the same as modulus of Z1 alone plus, divided by modulus of Z2 alone. So modulus of Z1 is that, modulus of Z2 is this. So simplify, we'll come up with this. So here we can't stop here because it is not possible for you to leave a third in the denominator. So always the final answer must never have a third in the denominator. So what we do, we also rationalize by multiplying both the numerator and denominator by this. That's why we come up with this. So Roman 2, modulus and argument of the whole of this. So here it has plus, so meaning that you can't use the other shortcut. You have to go the long way by expanding. So when you expand, we shall come up with that, open brackets to come up with that, and simplify further to come up with this. Now that I have the, in terms of A and B, I realize that this one is now in the fourth quadrant because positive real, negative imaginary. The modulus is easier because it's square, this squared plus this squared, everything under square root to come up with this. So now argument, we must realize that it lies in the fourth quadrant, therefore the argument will be negative arctan imaginary over real. So I believe by now you know why we are putting this magnitude sign. Now when I use a calculator, I'll come up with this as the argument. So now we shall go to locus of a complex number. So the locus of a complex number, z equal to x plus yi, is the path taken by a variable point pxy. I think you realize that this x is the same as this and this y is the same as this, of that complex number according to the set conditions. Know this word, set conditions. So we already covered the much about loci, and it's available on this platform and the section of algebra, so I shall not repeat what you already covered. We are going to just deal with this part which requires complex numbers. So the conditions which we talked about here can be divided into 4 parts. One is the condition on modulus, so they can give you a complex number and tell you to get this locus based on a given condition on modulus, or condition on argument, or condition whether it's purely imaginary or whether it's purely real. So purely imaginary means that the real part is 0, and purely real means that the imaginary part is 0. I think you remember that on the introduction of this video. So we have already seen what modulus is, so there's nothing to write about modulus. Let's just go to questions. So question 1 came from UNEB 2015 paper 1 question 11b and says Roman 1, find the Cartesian equation of the curve given as this. In other words, the one the locus the Cartesian equation. Then part Roman 2, show that it represents a circle and find the center and radius of the circle. So the good thing is that even the topic of circles already covered on this platform. Okay, so let's start with question 1. First of all, the first thing to do is to write this and to remember that z is equal to x plus yi, but we are the one to let it because it's not a mass. So we shall first say let z be equal to x plus yi. Then from there we shall quote this condition given. Now this is what we meant by condition on modulus. Then we shall substitute for z and then simplify by collecting like terms, this and this real alone and imaginary alone, real alone, imaginary alone. Then from there we shall remember how to get the modulus of a complex number, because this one now we have real, imaginary, imaginary, real, imaginary. So modulus is easier because you square each and put it under square root. So let's see that in the next slide. So to be this square plus this square, everything under square root, then 2 times this square plus this square, everything under square root. Then from there we're going to remove the square root by squaring both sides. So when I square this side, the square root goes away and remain with this one alone, which I can expand. So when I expand this, I'll come up with from here up to here. Then expand this, I'll come up with from here up to here. Then for this one, 2 squared gives me this 4. Then this one gives me from here up to here. This one expanding it gives me from here up to here. Okay. Next is to simplify further by opening this bracket to come up with this line. Then after that we have to collect like terms and put everything on one side. So here this will be the Cartesian equation they wanted. Now let's go to Roman 2. Roman 2 said, show that it represents a circle and hence find the center and radius of the circle. So for you to show that it represents a circle, you have to realize that the coefficients of x squared and y squared are the same and the rest of the terms are linear. So when that happens, it implies that the Cartesian equation represents a circle. Then for the other part, for the part of radius and center, you have to compare this with the general equation of a circle. Then you shall realize that 2g is equal to negative 20, therefore negative 20 over 3. Why are we saying 20 over 3? Because if you look at this one, the equation of x and y is 1, yet here it is 3. So what you do, you have to first divide throughout by 3 to come up with negative 20 over 3, which is here. Then therefore g will be negative 10 over 3. Similarly, 2f is 14 over 3, therefore f is 7 over 3. And c is 7 over 3, which is here. Now after getting g, f and c, we can easily get the center and radius. So center is negative g, negative f, which is that. And the radius is given by this formula, g squared plus f squared minus c. We already saw that under the topic of a circle. So in the end we shall come up with this as the radius of our circle. So question 2 came from UNEB 1999 paper 1 question 11 Roman 1 and says, if z is a complex number, describe and illustrate on the Argan diagram the locus given by this. So this, like I said, this is what we call the condition on modulus. So what we should do, we shall first let z equal to x plus yi, then come and quote our condition and substitute for z. Here we shall simplify by collecting like terms together. Then we can cross multiply, take this one this side, come up with this line. After that we can get our modulus. So modulus is this squared plus this squared, everything under square root, this squared plus this squared, everything under square root. You don't forget this 3. Then after that we are going to square both sides. So when you square both sides, we shall come up with this, because this power will go with this square root to remain with this, which is that, and this power 3 to power 2 is 9, that's why you see 9 there, and for this one it goes with the square root to remain with this part, which is here. Next is to open this box bracket to come up with that, and after that we have to collect like terms by rearranging everything on one side. When I divide throughout by 8, I come up with that, which is the equation of the circle. Therefore the locus is a circle. But they told us to illustrate it on an Argand diagram. So now I think realize that now we no longer have real and imaginary, we only have xy, meaning that now the axes will no longer be real and imaginary, the axes will be x-axis and y-axis. So let's see that in the next slide. So for the circle, you have to know the radius and also the intercepts before you sketch. So from this, by comparison with this, G is this, and F is that, then C is that. Therefore, the center will be given by that. After getting the center, I have to get the intercept. So intercept is when x is 0, I'll come up with that. Therefore, using Bulldozer method, y will be undefined. Now here, previously we have been putting there a complex real and imaginary part, but now here, because we are sketching on the axis, we have to maintain that it's undefined, because there's no way you'll show the value of y on x-axis and y-axis. If it was real and imaginary, it would be easier, but now it is not possible. So that is why we just say undefined, and therefore we conclude that there is no y-intercept. What about when y is 0? When y is 0, substitute to come up with a quadratic, use Bulldozer method, you'll come up with those values of x. Therefore, you'll conclude that the intercepts are this and this. Now we have the intercepts and we have the center, meaning we can now sketch our circle. So in summary, this is what we have got, and that is what is going to help us to sketch our circle. So we have to draw the axes. This time we label x-axis and y-axis. We no longer label real and imaginary. It has to be x-axis and y-axis. Then we have to locate the intercepts and also the coordinates of the center. So coordinates of the center are these ones, and that circle passes through this point and this point. Therefore, if you draw a circle that it passes through this point and this point, and that's what they wanted. Then question 3 came from UNEB of March 1998, paper 1, question 10a, and says, show the region represented by this on an Argand diagram. In other words, they want you to first get the locus. So we shall first let z be equal to x plus yi. Then come and substitute for z. Then rearrange to come up with that. Then get the modulus, square both sides, and this shows that the locus is a circle with center this. So center will be go from here, this will give you 2, this equal to 0 will give you 2, this equal to 0 will give you -1. And the radius is here, because what is here will be r squared. I think that's what we saw under the topic of circles. So if you are not confident where it comes up, how it comes about, it's better you go and review that topic of circles. Like I said, if you want to sketch a circle, you have to get the center and also get the intercepts. Now I've got the center, but what about the intercepts? I'll come and say that when x is 0, put 0 here, you'll come up with that part. Therefore, make y the subject, and you realize that y is undefined because square root of a negative becomes complex. And here we don't write in real and imaginary when you are sketching on x and y axis. So we just say there is no y-intercept. What about when y is 0? When y is 0, put 0 here. You'll come up with that. Therefore, simplify, make x the subject, and x will be 2. Therefore, the intercepts are 2, 0. So now that I have the intercept and the center, I can sketch the locus or the circle. Okay, so remember in the question they gave us an inequality, it was not equal to, so you have to know the region which is unwanted and shade that. So the unwanted region, first go back to the equation of the circle, and what you do, you are going to use the coordinates of the center, because that one you are very sure that that coordinate is inside the circle. So coordinates x is 2, y is -1. So when I use them and substitute them here, I'll come up with this. Therefore 0 will be less than 2, sorry, 0 is less than 1. So ask yourself, is this true or false? It is true that 0 is less than 1. So now when you get true here, it means that where you got that point is the wanted region. So remember, the center is always inside, meaning that the inside part is the wanted region and the unwanted is the one which is outside. So when you are shading, you are going to shade the outside part. Then 2, the inequality is just less than, meaning the circle has to be dotted. So we shall come and sketch our circle. Draw the axes, label them, put the necessary points, then locate the center, and then draw the circle. It has to be dotted. Then from there I have to shade the unwanted region, and basically that is what they wanted. So now we shall go to question 4, which came from UNEB 1990, paper 1, question 3b, and says, find the Cartesian equation in its simplest form of the curve described by this condition. So this is the conditional modulus, where w is the complex number x plus y plus iy, and then sketch on the Argand diagram the region satisfying this inequality. So let w be that. So anyway, here it was already given, but still, even if you write it, it doesn't change anything. So we know that w is that, therefore come and quote the condition, then substitute for w, and after that you rearrange. Then from there you get the modulus and square both sides to come up with that. Expand further this one and this one also. Then collect like terms to put everything on one side. You can divide through by 3 to come up with that. And that is the Cartesian equation in its simplest form. They said in its simplest form. And that locus, it will be a circle, or the Cartesian equation is the circle. Now for the sketch, we have to get the center and also the intercept. So for the center, by comparison, 2g is 2, therefore g is 1, and also 2f is -4, therefore f is -2. Therefore the center is -1, 2. I believe by now you know where it comes from. Now for the hence part, we have to get the unwanted region. So from here we shall substitute for this and this. We already saw them in the previous slide. Therefore, using the center as a point, therefore we are going to substitute for x and y. We shall come up with false. Now when we come up with false, it implies that where you got that point from is the unwanted region. So the center is always inside, meaning that now this one is the unwanted region, and that's what we shall shade. Then after that, you also realize that the inequality is less or equal to, meaning that the circle will be a full line. It is no longer dotted. Okay, so the intercepts, we also need the intercepts. So when y is 0, we shall come up with that, and therefore x will be that. Then when x is 0, we shall come up with that, and y will be that. Therefore the intercepts are, now we have many intercepts. There are 4. There is this 1, 2, 3, and 4. Okay, now that we know the intercepts and we know the center of the circle, we can go ahead and sketch our circle. So in summary, this is what we have got, and that's what is going to help us to sketch our circle. So we have to draw the axes and label them. Now this time we use x and y axis. Then show the necessary points. All these points must be located. Okay, so after that we shall locate the center of the circle, and we shall draw a circle so that it passes through all those intercepts. Then from there we shall remember that the unwanted region is inside the circle, so we shall shade inside the circle. And basically that is what they wanted. Then question 5 came from UNEB 2013 paper 1 question 9b and says, what are the greatest and least values of this if z is that, if z minus 4 is less or equal to 3? So let z be equal to that. Therefore come and code the condition, then substitute, and then you'll come up with get the modulus, then square both sides. So the locus is a circle and the center is 4, 0. Radius will be 3 in case it was needed. But we need the center and we're interested in the center and the intercept. So intercept, when x is 0, we shall come up with the value of y as undefined. Therefore no y-intercept. And when y is 0, we shall come up with the value of x as 1 or 7. Therefore the intercepts are these ones. Okay, we have got the intercepts, we have got the center. We also need to know the unwanted region. So the unwanted region, we shall start from here and substitute for x and y. So using this center, and we shall come up with 0, which is less or equal to 3. And this is true, meaning that where you got that point is the wanted region, so we shall shade the outside region. Now we shall go and make our sketch. Draw the axes and label them. Then show all the points which are of interest. Then locate the center of the circle and draw a circle to pass through those points. Then shall remember that you are going to shade the outer region, so let's do that. Then from there they ask for minimum and maximum values. So the good thing, the center passes through the axis, therefore this will be the least value and this will be the greatest value. So shall come and conclude that least value is 1 and greatest value is 7. And that's what they wanted, because modulus over complex number is equal to the modulus of its conjugate. So yeah, that means that this one is also the same value for the conjugate of that complex number. That was condition on modulus. Now we shall go to the condition on argument, and the good thing, we already know what an argument is. So as a reminder, you have to remember that argument is arctan of imaginary over real. When you remember that, then you can easily go through these questions. So let's start with question 1, which came from UNEB 1999 paper 1 question 11 Roman 2. So it says, if z is a complex number, describe and illustrate on the Argan diagram the locus given by this. So this is the condition on argument. Therefore, like we have done before, we shall say let z be equal to x plus yi, then code the condition on argument, then substitute for z, rearrange. Then from there we shall remember that argument is arctan of imaginary over real, so imaginary is y and real is x plus 3. Then take turn this side to come up with this. Now this argument is in radians, therefore tan of pi over 6 is the same as 1 over root 3 standard partial angles. Then cross multiply, and that will be the locus. So the locus is a straight line, but they wanted you to describe, this is what you have described, straight line, but they also wanted you to illustrate it on the Argand diagram. So for a straight line we need any 2 points, and we just join those 2 points. So we shall come here and use the intercept. So when x is 0, y will be that, and when y is 0, x will be that. Therefore the intercepts are those ones, and those are the ones we shall use to sketch, to draw our line. So come and draw the axes and show the necessary points, then draw a line passing through those two intercepts. But care must be taken for this line not to penetrate this part. If it goes this side, it will change everything. Now how does it change everything? Because from this side the argument is still this positive, but when it goes this side the argument is going to change, it will become this. Okay, so I believe you realize why we don't exceed this point. Okay, then question 2, sketch the locus of this for the point representing z equal to x plus yi. So here the a plus to define our x and hence determine the minimum value of modulus of z. So argument of this is the conditions, then substitute for z, rearrange, then get the argument is arctan imaginary over real, then take turn this side to come up with that. Note that there's a negative, so don't forget it. So arctan of negative pi over 4 is the same as negative 1. Then you cross multiply and rearrange to get the locus. So we shall say that the locus is a straight line with a negative gradient. But they also wanted you to get the minimum value of z. So okay, they wanted you to sketch. So let's first do the sketching. Sketching, we need the intercepts. So when x is 0, y is negative 1, and when y is 0, x is negative 1. Therefore the intercepts are those two. So let's go and sketch now that we have got the intercepts. So we shall draw the axes and label them, then show the points which are necessary, and then draw our line. Now here also care must be taken. This line must never exceed this point to go this side, because if it goes that side the argument is going to change to become this, which is positive. But in our case, the question the argument given was negative, so it has to be like this. So always remember never to cross this axis. Okay, now from there we shall now conclude that this is our minimum value. So we shall come and quote that magnitude of z will be 1. Now why are we saying 1? Because magnitude means that what is negative becomes positive. So here it was negative 1, it has become positive 1. Okay, so question 3 says find the locus defined by this, where z is a complex number or x equal to x plus yi. So still here they have defined for us what z is. So what we are going to do, we are going to first extract out this one and simplify it, because when you look at this one the denominator also has an imaginary part. So we have to first rationalize so that the imaginary part is no longer in the denominator. So when you expand, simplify, we shall come up with that part. Rearrange, you come up with that. So now we have separated the real alone and imaginary alone. So once we have that, we shall come and say that real part is this, which is the whole of this over this, then imaginary part will be this over this. Therefore after that we shall remember that argument is equal to arctan of imaginary over real. So I'm going to get this imaginary divided by this real, and when I do that I'm going to come up with this. So this one cancels with this, that's why you don't see it anywhere here. Then from there I'm going to take this, turn this side. So let's see that in the next slide. So take turn this side to come up with that, and tan pi over 4 will be positive 1. Then cross multiply and rearrange to come up with this locus. So the locus is a circle. Then question 4, find the locus of z given that arg this is equal to pi over 4. So still the same procedure, we first extract out this and simplify it because the denominator has an imaginary part, so you have to first rationalize and expand and simplify. Okay, so when you simplify, we now have the real part and the imaginary part. Now that we have got the real part and imaginary part, we shall go back to this argument. Let's see that in the next slide. So you come and say that from this, argument is equal to arctan of imaginary part over real part. So substitute for imaginary and real to come up with that. Then take this tan this side to come up with that. Then tan pi over 4 will be positive 1. Then cross multiply to come up with that. Then collect like terms and put everything on one side to come up with that, and that will be the locus, which is a circle. That was the second condition on argument. Now the third one will be on purely real condition. We saw that purely real means that the imaginary part is 0, so there's nothing to write apart from that. So let's go straight to the question. So question 1 came from UNEB 2017, paper 1, question 9b, and says prove that if this is purely real, then the locus of the point representing the complex number z is a straight line. So they want to show that the locus is a straight line. So first of all, we are going to come and substitute for z. Then after substituting for z, we realize that the denominator has an imaginary part, meaning that we have to rationalize, which is this. Then expand to come up with this. After that, we shall rearrange to come up with that. Okay, let's go to the next slide. Collect like terms, put real alone and imaginary alone. Then from there we shall know that the real part here is that and the imaginary part is that. Then we shall remember what they told us. They told us that it's purely real, meaning that the imaginary part is 0. So the whole of this will be equated to 0. So when I do that, when I cross multiply the whole of this by this will give you 0, so we'll come up with this, rearrange, and to be a straight line. Then question 2 came from UNEB 2016, paper 1, question 9b, and says given that the complex number z given that complex number, Roman 1 find this, and Roman 2 show that the locus of this is a straight line when its imaginary part is 0. So in other words, purely real. And state the gradient of the line. So let's start with Roman 1. So Roman 1, we shall come and substitute for z. So here, even if you interchange, there is no problem because it's a product. That's why here it was IY and here I'm using YI. It's the same. So the denominator has an imaginary part, meaning you have to rationalize. Then you expand. After expanding, you have to look for a way of simplifying. Then you come up with this, and that's what they wanted here. As long as there's no imaginary part in the denominator, you are good to go. So now we shall go to Roman 2, where they want you to show that the locus is a straight line when the imaginary part is 0. So what you're going to do, you will extract out your imaginary part and equate it to 0. Then cross multiply and rearrange to get the equation of a line. So you have shown that the locus is a straight line. They also wanted the gradient. Gradient will be this, which is that, and that's all. Then now shall go to the last part of under locus, which is purely imaginary condition. So this is the opposite of purely real. Purely imaginary means that the real part is 0. Therefore, there's nothing to write apart from that. So we shall come and say that question 1, find the locus of the point representing the complex number z, given that this is purely imaginary. So we shall come and first let the z be equal to this, then substitute for z. the imaginary part, the denominator has an imaginary part, so you rationalize and expand, then simplify by simplify, and then we have to collect like terms, collect real alone and imaginary alone. Let's see that on the next slide. Okay, after separating the two, I'll come and say that real part is this and imaginary part is that. Therefore, for pure imaginary, real part is 0. So I'm going to get the real part and equate it to 0. Then cross multiply, and that will be the locus they want. So we have been looking at loci. Now we shall go to the next part, which is modulus argument form of a complex number. So we have been expressing complex numbers in terms of real part and imaginary part. So now we are going to see, is it possible to express them in terms of modulus and argument? So here we shall consider a complex number z equal to a plus bi, which is the usual form we have been knowing, because we have been expressing complex number in terms of real part and imaginary part. So let's first sketch its Argand diagram. So here we shall use real z because it is in terms of real and imaginary, and im z. Then both are positive, meaning that in the first quadrant, so we shall put their points and then locate the complex number. So this number now, where there is now this theta is the argument and this r is the modulus of this complex number. So from here t it is a units, and from here t it is b units, which is here. Therefore we realize that I have got a right angled triangle, and with that right angled triangle I can get the expression of cos theta and sin theta. So cos theta is equal to adjacent over hypotenuse, which is a over r. Now when I make a the subject, it will be r cos theta. What about sin theta? Sin theta will be opposite over hypotenuse, which is b over r. Now when I make b the subject, I'll come up with r sin theta. Therefore, where r is the modulus of z, in other words, r is equal to modulus of z. Now substituting for a and b in this expression, I'm going to come up with, this is a and this is b, there is I is maintained. So pulling out r, because it is common, I'll come up with this expression. Now that is what we call the modulus and argument form of a complex number. It has r, which is modulus, then cos theta plus I sin theta, where theta is the argument of that complex number. So always remember, when they tell you to express a complex number in modulus argument form, they want it to be in this form. Now there are some special concepts we need to know here. So if z1 is a complex number with modulus r1 and argument theta 1, it can be expressed in modulus argument form as this. Then also if z2 is a complex number with modulus r2 and argument theta 2, it can be expressed in modulus argument form as this. Now there it implies that when I multiply the two complex numbers, the modulus will be multiplied together to give you this, but the argument will be added. I think remember that argument is as if you are dealing with a logarithm. So when I multiply the two, log a times b gives you log a plus log b. That is why the argument have to be added, but the modulus are multiplied. That is for multiplication. Then when it comes to division, still the modulus are divided in correct order. Z1 and also Z1 has modulus R1, Z2 has modulus R2. But when it comes to argument, they are subtracted. So this is the argument of this is the first minus argument of the denominator. So always remember that, because it is going to be used more frequently in the questions which will arise. So the modulus argument form of a complex number is also sometimes referred to as the polar form of a complex number. So when you hear this word polar form, don't see it as a strange word. It is the same as modulus argument form. So now shall go to question 1, which came from UNEB 2013, paper 1, question 9a, and says the complex number this, and this is its conjugate. Roman 1, express z in modulus argument form. Then Roman 2, on the same Argan diagram, plot this and that. Okay, so first of all, it starts with Roman 1. For this one, modulus is that, and argument will be that, because this is the first quadrant, therefore to be arctan imaginary over real, and to be 30 degrees. So now that I know the modulus and argument, I can express it in terms of modulus argument form, modulus and argument here. Don't forget this I. That is Roman 1. Roman 2, so Roman 2 shows that z, the conjugate of z, here it means that the sign changes to minus, and therefore this one becomes this. Open brackets to come up with that. Therefore, when I'm sketching on the Argan, now I'm going to use real and imaginary, because that is what I have. I have a real part, imaginary part, real part, and imaginary part. So I'll put the necessary points. Then I'll first locate this one, root 3 and negative 1, to give me the complex number of z conjugate. Then I'll locate this and this to give me this complex number. And that's what they wanted. Then question 2 came from UNEB 2012, paper 1, question 19, and says, if z is equal to this, part A, find Roman 1, the modulus of z, Roman 2, argument of z, and part B, represent z on a complex plane, and part C, write z in polar form. I think we realize that now they are saying polar form instead of modulus argument form. They all mean the same. So let's start with part A. So part A, this is z. So the modulus, it means that you can get the modulus of this alone, which is this, modulus of this alone, which is here, and modulus of this alone, which is there, and this power will come after that. So modulus of this is that, modulus of this is that, modulus of this is that, everything raised to the power 2. Simplifying will give you this as the required modulus of z. That is Roman 1. What about Roman 2? Roman 2, they want argument of z. So argument of z is equal to this plus this, because it was product, now it becomes plus, then over this, because it was division, now it becomes minus. It was square, no, so that square comes here, the power 2 comes down. So now after that we shall realize this one is in which quadrant. It is in the fourth quadrant, so it will be arctan imaginary over real. This one is the first quadrant, so it will be, sorry, this will be negative arctan imaginary over real. I believe by now you know why we are putting this magnitude. Then this one is in the first quadrant, so it will just be arctan real imaginary over real. Then this one is also first quadrant, so it will be arctan imaginary over real. Then use the calculator to come up with that, and that will be the argument they wanted. So now we shall go to part B. Part B, they said represent z on the complex plane, so that means the Argan diagram. So I draw the real part, real z, imaginary z. So this argument is negative, meaning it is in the clockwise direction. That's why you see it going in that direction. Then this is the modulus of that which we got, so that represents z. Then now shall go to part C. Part C says write z in polar form in terms of modulus argument. So shall just come here and write that z is that, modulus is this, argument is that. So when you simplify, cos of a negative angle is the same as positive cos that angle, and sine of a negative angle is the same as negative sine of a positive angle. That's why here it was minus, it was plus, now it is minus. Then question 3 came from UNEB 2001 paper 1 question 9b and says express this in modulus argument form. So z is that, therefore modulus will be modulus of this over modulus of this, which gives you this. But the side cannot remain in the denominator, so you rationalize to come up with this as the answer. Then argument will be this minus that, which is that. Therefore argument of I is 90 because it is purely imaginary. Then this is a positive first quadrant, so it will be arctan that. In the end you come up with 33.69 degrees. Therefore in modulus argument form, modulus is this and argument is that, and that's what they wanted. Then question 4 came from UNEB 1992 paper 1 question 4b and says given that z1 is that, z2 is that, express z1, z2, z1 plus z2 and z2 minus z1 in the form r in brackets cos plus I sin theta. Then Roman 2, determine the angle between this and that. Okay, so let's start. So for z1 we shall first get the modulus and also the argument. Then also therefore z1 is in that in terms of modulus argument form. Then for z2 also get the modulus, get also the argument. So this one is in the second quadrant, that's why it is 180 minus arctan. Then write in modulus argument form. Then you also have to get this and this. So z1 plus z2 is that, you end up with 2 plus 6i. Then z1, therefore magnitude will be that, and also argument will be arctan real imaginary over real. What about, therefore in modulus argument form it is this. What about for subtraction? Subtraction gives you this, therefore magnitude will be this and argument will be this. Therefore in modulus argument form it will be that. Simplifying, here you can simplify to become a minus when the angles are positive. Then for Roman 2, the one the angle between this and that. So here we have to just subtract the two angles and come up with this as the angle between them. So now we shall go to question 5, which came from UNEB 2006 for 1 question 9a and says express the complex numbers this and this in the trigonometric form this, and hence otherwise evaluate that. So for this one, modulus is that, and for this one, modulus is that. Then argument of z1 is purely imaginary, so it will be 90 degrees. Then for argument of z2 it will be, this is the fourth quadrant, so it will be negative arctan, which gives you negative 45 degrees. Therefore z1 is this and z2 is that. But they wanted this division, so division, let's do that in the next slide. So for the hence part, so this one, because cos of a negative angle is positive cos of a positive angle and sine of a negative angle is negative sine of a positive angle, that's why here it was plus and here it is minus. Then for the hence part, we shall say that z1 over z2 squared is the same as this over this squared. So this squared means that the power will be, the modulus will be squared, but the argument will be multiplied by 2. Simplifying gives you that. When I divide two complex numbers, the arguments are subtracted. So 90 minus negative 90 gives you 90 plus 90. That's why you see a 90 plus 90. But the modulus are divided. I think we already saw that. Therefore, in the end, we shall come up with that. And simplify to come up with this as the required answer. So now we shall go to DEMOVRE'S theorem. So DEMOVRE'S theorem states that if z is equal to r in brackets cos theta plus I sin theta, then it implies that z to the power n is the same as the whole of this raised to the power n, and which is also equal to this power goes to this, which is that, and this power multiplies the angle to give you n theta and n theta there. So that is what we call DEMOVRE'S theorem. Similarly, if it is a negative power, it is the same, the negative power is there, so it goes on the modulus and also multiplies the angle by negative power. And in the end, we shall come up with this, because this one gives you negative sine n theta. Now we are going to do something. If r is equal to 1, the expressions now are going to become that. Okay. Now what we are going to do, we shall say what will happen if we add the two angles. So when I add the two equations. When I add the two equations, you will realize that this and this cancels, you remain with this plus this, which is that. So we have subtracted the two equations, but what if we we have added the two equations, but what if we subtract them? So equation 1 minus equation 2, this is what we are going to come up with. So what happens? This cancels with this, remain with this and this, which is that. So these are this is equal to this and this is equal to this. That's what you should always remember in this topic of DEMOVRE. Then also remember that this is equal to this, and also this one is equal to this. So those are the four equations you need to remember in this topic. So we shall use them more frequently through the worked examples so that I can easily grasp them. So let's start with question 1, which came from UNEB 2004, paper 1, question 15, and says, without using tables or calculator, simplify this. So the first thing to realize is that they are somehow similar, but this is plus and this is minus. So what do? To make this one also plus, you have to take this back here and here. I think remember that. So when I take it back here and here, I'll come up with now a plus. After that, I'm going to take, now this one is as if it is negative 1 times pi of 17, negative 1 times pi of 17. So what I'm going to do, I'm going to pull that negative 1 outside to come up with negative 9 here. So it's like we're doing the reverse of DEMOVRE'S theorem. So after doing that, you realize that now these are the same base. So same base, division means that you subtract the powers. So 8 minus negative 9 is the same as 8 plus 9. So 8 plus 9 gives you 17. Then from there, we are going to pull this 17 back here to come up with this and this. Then after that, this 17 can cancel and this can cancel to come up with this. Then from there, I remember that cos pi is equal to negative 1 and sin pi is 0. Then question 2 came from UNEB 2001, paper 1, question 9a, and says, use DEMOVRE'S theorem or otherwise to simplify this. Okay, so this is what we are given. So what I'm going to do, I realize that now here there is 2 theta, so I'm going to pull this 2, so this is 2 times theta, so I'm pull the 2 outside to come up with this power. Then also here it is a half times theta, so I'm going to pull a half outside to come up with this power. So what is inside the brackets are the same. So what I'm going to do, I'll use the rules of indices. So rules of indices, these are the same as this is power 1, so this plus this minus this, which is here. So using when I simplify this, either by using a calculator, I'll come up with 5 over 2. Now after that, that 5 over 2 will go back inside and multiply this and also with this to come up with this and that. And that's what they wanted. Then question 3 came from UNEB of March 1998, paper 1, question 10b, and says, express the complex number this in modulus argument form and hence find this in the form a plus bi. So z is that, therefore its modulus is that, and its argument is that, because this is in the fourth quadrant. Therefore in modulus argument form it is that. I can simplify to come up with that. Now for the hence part, z squared is equal to this, so modulus is squared, but the argument is multiplied by 2. You will come up with this. But I wanted you to express in terms of a plus bi, so this one is that and this one is that. Open brackets further, you come up with this as the value of z squared. What about 1 over z? For 1 over z, the same as 1 over this, so this is the expression of z in modulus argument form, which is the same as this to power negative 1. When I bring this one up, it becomes power negative 1. Then this negative 1 is going to enter inside to come up with this and this. So in the end I'll come up with, remember this one, sign of a negative angle gives you a negative sign positive angle, so that negative and this negative gives you a positive here. Then use this and use that, and this gives you that, and you open brackets to come up with this which they wanted. Then question 4 came from UNEB of March 1998 of November, paper 1, question 9b, and says, prove that for positive integer n, this is equal to this. In other words, they want you to prove DEMOVRE'S theorem, and deduce that this formula is also true for negative values of n. Okay. So we are going to use the method of proof by induction. So for n equal to 1, come and put here 1, you come up with this, which is that. Then for right hand side, where there is n, you put there 1, you'll come up with this. So they are equal, meaning that it is true for n equal to 1. What about for n equal to 2? Left hand side, put here 2, you'll come up with this, open brackets, you'll come up with this. Then from there, you'll rearrange this and this together. Why? Because there's an identity of these two. These 2 gives you cos 2 theta. Think you remember that under trigonometry. Then this 2, this sine and this cos gives you sine 2 theta, and this I is maintained. That is left hand side. What about right hand side? So the right hand side, it is where there is n, you put there 2 to come up with this, so it is true for n equal to 2. So now that it is true, we shall suppose, not this word, suppose. It is true for n equal to k. We are supposing because we cannot, there's no way we can prove it. So we shall just suppose, then we shall write that this is true. We are supposing that this is true. Therefore we shall now go to n equal to k plus 1. N equal to k plus 1, it means that where there is n, there was n, you are going to put there k plus 1. This one is the same as this times that. Splitting the powers. Then we already saw that this, we already saw from here that is true, therefore this one gives you this, and this one is the same as that, because it's power 1. Then I'm going to expand open brackets. This one multiplies everything here, and this one also multiplies everything there to give you this. Then open brackets further to come up with that. Then rearrange in terms of irregular part and imaginary part alone. Now this one is the same as this from factor formula, and also this is the same as this from factor formula. So it will come up with this. So when you come to the right hand side, where there was n, you put there k plus 1, k plus 1, and it is similar to the one of the left hand side. Therefore, we shall come and say that true for n equal to k plus 1. Now when that is true, you shall come and conclude that since it is true for n equal to 1, n equal to 2, n equal to k, and n equal to k plus 1, then it is true for all positive integers of n. So you have proved that's true for positive integers, but the question also wanted you to prove for negative, to deduce that's true for negative values of n. So what you are going to do, you shall come here and say that where there is n, we are going to put there negative n, and also here negative n. Therefore, from the left hand side, this one is the same as 1 over this from rules of indices. And we already saw that this one, we already proved that for positive n, this is okay, this is true. So we have got that. The next is to rationalize. Let us rationalize, because in the denominator here, in this denominator there is an imaginary part. Therefore we have to rationalize by multiplying by its conjugate. So it is positive, here we shall multiply by when it is negative, up and down. Then from there we are going to expand. So when I open bracket, this one with 2 squares here gives you this, and this one gives you that. Now you already know that this is an identity, that this one gives you 1. That's an identity of trigonometry. Therefore I'll come up with this. So that is left hand side. Now right hand side, this one will be equal to this, so they are equal. Now because they are equal, it implies it's also true for negative values of n. So now we shall go to question 5, which came from UNEB 2003 paper 1 question 12a, and says use DEMOVRE'S theorem to express tan 5 theta in terms of theta. So 5 theta means that there is going to be some expansion of power 5. So let's first do the Pascal's triangle of power 5. So how is Pascal's triangle done? You begin with 1, then put 1 on both sides, because what we want, it should come up with a triangle. That's why the word triangle comes in. Then from there put another one here, then here in between you add this plus this is 2, so you put 2 here, then here you put 1. Then put another one here, then this plus this is 3, so put 3 there, this plus this is 3, so put 3 there, and then put 1 to form a triangle. Then again put 1 here, then this plus this is 4, this plus this is 6, this plus this is 4, then put 1 to form a triangle. Then next put 1 here, then this plus this is 5, this plus this is 10, this plus this is 10, this plus this is 5, then add 1 to form a triangle. Now how do you know where to stop? This one is one which gives you the power. Now because we want to get the expansion of power 5, we shall stop here. If they wanted power 4, you should have stopped here like that. So that's where we're going to stop with that Pascal's triangle. Then we can now start answering our question. So from DEMOVRE'S, it will now be this power 5 equal to this. We already proved that. So I have to expand this to power 5, so open brackets. So that is why the importance of Pascal's triangle comes in. So how is Pascal's triangle used? Pascal's triangle helps you to get the coefficients. Okay, like for example this here, if you look at this, coefficient is 1, coefficient is 2, coefficient is 10, coefficient is 10, coefficient is 5, coefficient is 1, like that. Okay, that's the use of Pascal's triangle. Then the rest, it will be got by multiplying. So for example, what I will start with, if I start with cos power 5, I'll multiply it with sine, with this to power 0. So this power 0, it cancels away, so it remains with cos power 5 alone. Then I'll keep on reducing the powers of cos and increasing the powers of sine. So here to now it was cos power 5, here to be cos to power 4, and here it will be I sine to power 1. That is why now here you can see the expression of sine and this I there. We already seen how this one comes about. Okay, next, this one cos power 4, now to be cos power 3, and this one will increase to sine squared. Now we see this negative and we no longer see the I. Why? Because the power 2 is on both I sine theta. Now I sine theta squared gives you I squared sine theta. Now I squared is equal to negative 1. That is why you are seeing here a negative here. It is because of that I squared. Then next we shall go to this. This was cos cubed, now it will be cos squared, and so sine squared, now it will be sine cubed. Now I sine theta, everything cubed, gives you negative. I cubed the same as I squared times I, so I squared gives you this negative 1, and the remaining I is what we see here. The next, this was cos power 2, now to be cos power 1. This will now be sine to power 4. Now I sine theta to power 4, the I to power 4 gives you negative 1 times negative 1, because I to power 4 is the same as I squared times I squared, which is negative 1 times negative 1. That is why you see here positive, and there is no I anywhere. Okay, now this was cos power 1, here to be cos power 0, that's why you don't see any cos here. And this was sine power 4, now to be sine power 5. So I sine power 5, remember I to power 5 is the same as I to power 4 times I. I to power 4 was positive 1 already, so therefore that's why you see positive I here. Then this side is this other side here. Okay, so now we are done with expanding. Now we are going to compare real alone and imaginary alone. So when I start with imaginary part of this will be sine 5, and this side there is this imaginary, which is here. There is also this imaginary, which is here, and also this imaginary, which is there. Okay, what about the real part? This side there is this real, which is here, and this side there is this real, which is here, and this real, which is here, and this real, which is here. Those are two equations. Therefore I can now get my tan theta, because I know that tan theta is equal to tan 5 theta is equal to sine 5 theta over cos 5 theta. So I'll come and divide the two equations. So when I divide, I'll come up with that. Then next, this one gives me tan 5 theta. Then this one I'm going to multiply up and down by 1 over cos 5 theta. So when I do that, this with this will give me tan 5 theta. Then the whole of this with this, then the cos squared is going to cancel here. This would now become tan cubed. Okay, then for here this cos power 4 will cancel, then here to now become tan theta. That is numerator. What about the denominator? This and this, it will cancel to give me 1. Then this with this is going to cancel to give me tan squared theta. Then this with this will cancel to give me tan power 4 theta. And that's what they wanted. So now we shall go to question 6, which say that given that this is equal to this, I think we already saw that, solve this equation. Now there is something about this equation, and this type of equation is called a cyclic equation. What is special about this equation? If you look at this with this, it is the same coefficient. Look at this with this, it is the same coefficient, and this one is at the center. So such equations are called cyclic equation. Now when that happens, when the coefficients are the same, it implies that you can easily use this concept to solve them. How do we do that? Let's get started. So first I'm going to pull out z squared. When I pull out z squared, this will become this will become this becomes this becomes this, and this becomes that. Okay, next it means that either this is 0 or the whole of this is 0. So I've dealt away with this. Okay, now let me work with this. Now for that one, I'm going to rearrange so that the coefficients which are the same, put them together. So there is this 5 and this 5, pull them together. Okay, then there is this one and this one, pull them together. Then you remain with this one which is alone. Okay, when that is done, you are going to factorize out, because here 5 is common, here negative 11 is common, pull them out. When you do that, you are going to realize something funny, that somehow in that form. When you realize that, then you can now use it. So you shall come as that. From this, it implies that when here it is, when n is 1, I'm going to come up with this, and when n is 2, I'm going to come up with this. Now what I'm going to do, I'm going to substitute for that. So where there is this, I'm going to put there this, and where there is this, I'm going to put there that. Okay, so let's do that. So I'm put this here and put this there. Okay, now we can go to the next slide and see what happens. So open brackets to come up with that. Now this one, now it's like a trigonometrical equation which I have to solve. So this one expanded to give you that. Those are double angle properties, and the video of trigonometry is available on this platform. Then open brackets to come up with that. So I'm coming up with a quadratic in cos theta. Therefore, I can easily solve it. I can either use factorization or Bulldozer method. So in this case, I've used factorization, and when I factorize, I'll come up with that, implying that cos theta can be this or this. But I already know that this one is equal to 2 cos theta. What does that mean? It means that this will be that, and remember this power negative 1 is the same as 1 over z. Therefore, I'm going to multiply by z to come up with that, rearrange to get a quadratic, use Bulldozer method to solve the 2, and then I'll come up with the value of z. Then do the same for the other value of cos theta. So for the same procedure, so get the quadratic in z, use Bulldozer method, and simplify to get the value of z. So those are the 4 roots of z of the given quadratic equation. Okay, so now we shall go to question 7. It says use DEMOVRE'S theorem to show that this is equal to that. So by Pascal's triangle, because of this 6, we need the Pascal's triangle because there's going to be an expansion of power 6. So these ones you already know them up to power 5. So let's just write them. Okay, so that is where we stopped in the previous question on Pascal's triangle. So next put 1 here, then this plus this gives you 6, this plus this gives you 15, this and this gives you 20, this and this gives 15, this and this gives 6, then put 1 to complete a triangle. So we shall stop there because we have got our power 6 there. So we shall come and start from this. We know that this is equal to this. That when I power 6 on both sides, I'll come up with that. Okay, expanding this one is easier because 2 to the power 6 times cos to the power 6 theta. But this one I'll need this Pascal's triangle. Remember we said Pascal's triangle helps you to get the coefficient. So this is 1, that's why there's 1 there. Then there is 6 there. There is 15. There is 20. There is 15. There is 6. And there is 1. That is all about Pascal's triangle. The rest, let's see how they are generated. It is you to choose where to start from. So if I start with this one with the highest power, it will become this, power 6, and this will be power 0. So it's as if we are saying z power negative 1, everything raised to power 0 to come up with this. Here it was power 6, so it will be power 5, and here it was power 0, so it will be power 1. So z power negative 1, everything raised to power 1 gives you z power 1. Okay, then here it was power 5, so it will be power 4. Okay, let's not confuse them. Let's start with this positive power. So this was power 6, so it would be power 5, power 4, power 3, power 2, power 1, power 0. Okay, then the negative powers: power 0, power negative 1, power negative 2, power negative 3, power negative 4, power negative 5, power negative 6. So that is how Pascal's triangle can be of good help. Next is to use rules of indices. So this gives you this, same base, it gives you this, separate the powers. Same base, you're going to subtract to give you this. Same base, you're going to subtract to give you power 0. That's why you only see 20. This one, you come up with this. This one, you come up with this. This one, you come up with that. Okay. The next is to rearrange the powers, similar powers. So this positive and negative power, positive and negative power, positive and negative power, and a constant. So that means that is now something like cyclic. So therefore I'm going to substitute. So this one means that here n was 6. Here it means that n was 4. Here it means that n was 2. Now expand this one, you come up with 2 to the power 6 is 64, and this becomes cos power 6 theta. But they want this one the subject, so I'll bring this 64 the other side, and that's what they wanted. So now we shall go to another part, which is the kth root of a complex number. Now kth root means square root, cube root, fourth root, and so on. But usually we stop on fourth root. So we shall consider complex number a plus bi. The kth root of this complex number can be got using the steps below. So there are some steps which should be followed for you to get the kth root of a given complex number. So let's look at those steps. The first step says calculate the modulus and argument of the given complex number. I believe by now you know how to get the modulus and argument of a given complex number. So step 1 is okay. The modulus can either be in degrees or radians. I think I've already told you that. Sorry, I said modulus. No, it should be argument. The argument can be either in degrees or radians. So let us first consider argument in degrees. So we are going to first write the steps where the argument is in degrees. Then at the end we shall put a note where the argument is in radians. What do you do? Okay, so that means that this one, the modulus of that is this, which is noted by R. Then the argument of this, remember it's first quadrant angle, so it should be arctan imaginary over real, which let it be theta. So that was step 1. Now let's go to step 2. Step 2 says obtain the general solution of the argument. Now here we have got a new term, general solution. Let's see what it means. And then express the given complex number in modulus argument form. So this one is okay, but this one general solution is not okay. So let's talk something about it. So using the general solution as the argument. So the general solution of the argument in degrees is got by adding 360 n to the argument where n is equal to 0, 1, 2, and so on up to k minus 1. So if k is 2, you stop at n equal to 1. If k is 3, you stop at n is equal to 2. And if k is 4, you stop at n equal to 3. That's what it means. So argument means that if you get this argument here, the general solution will just be got by saying theta plus 360n. So why do we do that? It is because, for example, if this is my first angle, the second angle will be got by first making a revolution, then go back to that place. There I've added 360. Then again I can do it two times, like that. So that is why we add 360 n. 360 means a revolution, and n means the number of times we're making a revolution. So that means that in modulus argument form it's going to become this, because instead of using argument I use the general solution of the argument. Then step 3 says put the power of 1 over k. Now this k, the value of k will be given the question. They will tell you find the square root. If they say find the square root, it implies that k is 2, therefore here you put 1 over 2. If they say find the cube root, it means that k is 3, meaning that you put 1 over 3. And if they say find the fourth root, it means that k is 4, therefore you put 1 over 4 on both sides, and use DEMOVRE'S theorem to simplify the expression that results. So let's see how this is done. So we're going to put 1 over k on both sides, then you simplify. Simplifying means this power goes on the modulus, and for the argument you multiply. So multiply 1 over k with this gives, that's why you see here over k. Multiply 1 over k with this gives, that's why you see here over k. And this one is the same as the kth root. You can either write it like this or write it like that. So that is step 3. What about step 4? Step 4 says substitute n equal to 1, 2, 3 up to k minus 1 to get the required roots of this. So like I said, if they say square root, it implies that k minus 1 is 1, therefore you stop here. If they say cube root, k will be 2, so you stop there. If they say if fourth root, it implies that you stop at 3. Like that. So we shall see in the questions. We shall look at all those cases: square root, cube root, and fourth root. So here they say, note that if you choose to express the argument in radians, remember radians, 360 degrees is equal to 2 pi radians. Therefore, where there is 360 degrees, you just put there 2 pi, but the rest remains the same. Okay, so now let's go to the questions. Question 1 came from UNEB 1995, paper 1, question 4b, and says find the square root of this. So that means that k is 2. So we'll come and say the first step is to get the modulus and argument. So modulus is this, and argument, this is in the second, negative, real, positive, imaginary. So it is in the second quadrant. So it will be 180 minus arctan. I believe by now you know why we put magnitudes here. So in the end, this will be the argument. So you have got modulus and argument, and that was step 1. Step 2, you have to first get the general solution of the argument. So it will be this argument plus 360n. In this case, we are using degrees. Therefore, writing in modulus argument form, I'll use its general solution here. Okay. The next is to raise both sides to power 1 over 2, because they said square root. So this is power 1 over 2, power 1 over 2. So that means that this one is the same as this, and this one means this, using DEMOVRE'S, this goes here to give you this, and this half multiplies the each angle. That's why you see a 1 over, you see a over 2 and over 2 there. Okay, so now next is to go to the last step of substituting. So for n equal to 0, substitute where there is n, you put there 0, you'll come up with this, and that means that this. So now here we're rounding off. Usually it would have been 4 decimal places, but something funny with this. If I say, let me first use the calculator. So if I get the calculator and I write root 13 times cos 56.31, I'm going to get 1.999996464. So when I round off to 4 decimal places, it still gives me 2.0. Then same applies to this, it will give me 3.0. That is why I'm using 1 decimal point. Then for n equal to 1, come and substitute, you'll come up with this. Therefore, in the end, I'll come up with negative 2.0 and negative 3.0i. And those will be the roots, because the square root has 2 values. So those will be the roots they wanted. Then now we shall go to question 2, which came from UNEB 2018 paper 1 question 10, and says express this in polar form. Now polar means modulus argument, and hence evaluate the cube root of this, giving your answer in the form a plus ib, where a and b are corrected to 2 decimal places. Now here they have specified the number of decimal places. If they don't, you use 4. So the first step is to get modulus and argument, which is that. The next step is to get the general solution and also the modulus argument form. The next, they want a cube root, therefore raise the both sides to power 1 over 3, 1 over 3. Therefore this side should be cube root, and this side use DEMOVRE'S theorem to get this and this. The next is to substitute. So for n equal to 1, I'll come up with this. Therefore use a calculator, I'll come up with this, but they said 2 decimal places, so I'll come up with that. Then for n equal to 2, I'll come up with that. Use a calculator, I'll come up with that. They said 2 decimal places, that's why I have to round off. For n equal to 2, I'll come up with that. Then use a calculator, I'll come up with that. They have to round off to 2 decimal places. So I'm going to stop at n equal to 2 because by default we have to stop at k minus 1. So cube root means k is equal to 3. Therefore 3 minus 1 is 2. That's why I have to stop at n equal to 2. And when I stop at that, I will have got all the 3 roots, 1, 2, and 3. Then question 3 came from UNEB 2008 paper 1 question 1 and says find the 4th root of 4 plus 3i. So get the modulus, get the argument, then get the general solution, then write the modulus argument form. Then raise both sides to power 1 over 4. Then use DEMOVRE'S theorem to get that, to simplify. After that, you are going to now to substitute. Start with n equal to 0, you come up with this. Use the calculator, you come up with that. So here they didn't specify, so you can use 4 decimal places. N equal to 1, come up with this. Use the calculator, come up with that. N equal to 2, you come up with this. Use the calculator, come up with that. N equal to 3, you come up with this. Use the calculator, you come up with that. So those are the 4 roots they wanted. And that brings us to the end of this video. So this video has marked the end of math paper 1. Next will be now math paper 2, and we shall start by remaking the video of descriptive statistics. So the videos of descriptive statistics are available, but their quality is wanting. That is why you have to remake them. So thank you for watching, and also if you know of any student who's not in this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so they can all benefit as a family.